Classical physics forms the basis of our understanding of the natural world before quantum ideas emerged. It began with observations and experiments by scientists like Galileo and Newton. They studied motion, gravity, and everyday forces, discovering that objects move in predictable ways. Newton's laws of motion explained how forces affect the movement of objects, whether it was a falling apple or a planet orbiting the sun. These laws rely on the idea that every object has a specific position and speed at any given time. In addition to mechanics, classical physics covers topics like light, heat, and sound. Light was once understood solely as a wave, with properties such as reflection and refraction, explained by scientists like Huygens and Maxwell. Maxwell's work even connected electricity and magnetism, showing that light is an electromagnetic wave. Thermodynamics, another pillar of classical physics, deals with energy, temperature, and the flow of heat, introducing concepts such as entropy. This framework of continuous and predictable behaviour allowed scientists to develop calculus, a powerful tool for analysing change. With these methods, classical physics became the cornerstone for many technologies, from the design of engines and bridges to the development of optical instruments. Though classical physics works well for everyday objects and large-scale phenomena, it could not explain everything. As scientists began exploring very small scales or high speeds, gaps in classical theories became clear. Nonetheless, the principles of classical physics remain essential for many practical applications. Its clear and orderly rules laid the groundwork for the revolutionary ideas of quantum mechanics that followed, providing a strong foundation from which modern physics has grown. Level 2. The quantum leap. The term, the quantum leap, marks the shift from classical physics to the new world of quantum theory. In the early 20th century, experiments began to reveal behaviours that classical ideas could not explain. One key observation was that energy does not flow in a smooth, continuous stream, but in tiny, fixed amounts called quanta. This idea changed the way scientists thought about energy and matter. Max Planck first proposed that energy is quantized when studying the radiation emitted by heated objects. Instead of being continuous, energy comes in small packets. This breakthrough led to a new way of understanding physical phenomena at microscopic scales. It was soon found that particles, like electrons and even light, can behave in unexpected ways. Sometimes they act like tiny, localized particles, while at other times they show wave-like behavior. The quantum leap introduced the idea of probability into physics. Rather than predicting exact outcomes, scientists now calculated the likelihood of different events. This was a major departure from the deterministic predictions of classical physics. It also meant that the behavior of very small particles could only be described in terms of probabilities, not certainties. This shift had a profound impact on both science and technology. Quantum theory led to the development of new devices such as lasers, transistors, and computers. These innovations rely on the understanding that matter and energy can exist in discrete states. The quantum leap thus opened the door to modern technology and forever changed our view of the universe. Level 3. Planck's constant. Planck's constant is a tiny, yet essential number that changed how we view energy. In the early 1900s, scientists struggled to explain how objects emit and absorb energy. Max Planck introduced the idea that energy is not continuous but comes in small packets. He found that the energy, E, of these packets is directly related to the frequency, F of the radiation, summarized by the equation E equals hf. Here, h represents Planck's constant. This constant set the scale for quantum effects. When energy changes occur in amounts comparable to Planck's constant, the classical view of continuous energy fails. Instead, energy is exchanged in discrete quanta. This insight solved the puzzle of blackbody radiation, where classical theories predicted unrealistic, infinite energy at short wavelengths. Planck's idea brought clarity and precision to these observations. Planck's constant also plays a crucial role in many quantum principles. It appears in the Heisenberg uncertainty principle, which tells us that certain pairs of physical properties, like position and momentum, cannot be known exactly at the same time. This principle is a cornerstone of quantum mechanics and shows how uncertainty is built into the fabric of nature. Moreover, Planck's constant is central to the Schrödinger equation, the fundamental equation describing how quantum systems evolve. Its small value means that quantum effects are usually hidden in everyday life, but become important at very small scales. This tiny constant has therefore opened up an entirely new understanding of the physical world, and has paved the way for modern technologies such as semiconductors and lasers. Through Planck's constant, we see that even the smallest number can have a profound impact on our understanding of the universe. Level 4. Photons. Photons are the basic particles of light and represent the quantum nature of electromagnetic energy. The idea of photons emerged when scientists discovered that light behaves not only as a continuous wave, but also as discrete packets of energy. This discovery helped explain phenomena that classical wave theories could not, such as the photoelectric effect. Each photon carries energy proportional to its frequency, as described by the equation E equals hf, where h is Planck's constant and f is the frequency. Higher frequency light, like ultraviolet, contains more energetic photons than lower frequency light, such as infrared. This simple relationship connects the microscopic world of quantum physics with the observable properties of light. Photons have a dual nature. They travel as waves and can interfere and diffract, creating patterns that we observe in experiments like the double-slit experiment. Yet, when they interact with matter, they behave like particles. For example, in the photoelectric effect, photons collide with electrons, knocking them out of metals. This particle-like behaviour was key to developing quantum theory. The discovery of photons has had lasting impacts on both science and technology. It led to the development of quantum electrodynamics, a theory that explains how light and matter interact with exceptional accuracy. Technological advances such as lasers, fibre optic communication, and solar panels rely on the principles governing photon behaviour. Photons are unique because they have no mass, yet they carry energy and momentum. This quality enables them to exert pressure and transfer energy over long distances. Understanding photons not only deepens our insight into the nature of light, but also drives innovations that power modern technology. Their discovery is one of the great milestones in science, bridging the gap between classical ideas and the quantum world. Level 5. Wave-particle duality. Wave-particle duality is a fascinating concept that shows how tiny objects like electrons and light can behave both as waves and as particles. In everyday life, we see objects as either one or the other, but at the microscopic level things work differently. Initially, light was understood as a wave because it could interfere and create patterns, much like ripples on water. Experiments such as the double-slit experiment demonstrated that light spreads out and forms interference patterns, clear signs of wave behaviour. However, later studies revealed that light also comes in small, discrete packets called photons. When light interacts with matter, for example, knocking electrons out of a metal surface, it behaves like a particle. This dual behaviour is not limited to light. Electrons, traditionally thought of as tiny, solid balls, also show wave-like properties. When electrons pass through narrow openings, they create interference patterns similar to those made by waves. This surprising discovery was captured in the de Broglie hypothesis, which proposed that every particle has an associated wavelength. The wavelength depends on the particle's momentum. The faster the particle moves, the shorter its wavelength. Wave-particle duality challenges our classical view of the world. In certain experiments, particles seem to travel along specific paths, behaving as discrete entities. In other setups, they spread out and interfere, showing a wave-like nature. This dual nature is a core idea in quantum mechanics, demonstrating that the behaviour of microscopic objects cannot be fully explained by classical concepts alone. Understanding wave-particle duality has led to many technological advancements. For instance, electron microscopes take advantage of the wave properties of electrons to capture detailed images at very small scales. This concept is also critical in developing quantum computers and other modern devices. In essence, wave-particle duality invites us to rethink the nature of reality, where objects can be both particles and waves, depending on how we look at them. Level 6. Quantum superposition. Quantum superposition is a foundational idea in quantum mechanics, stating that a quantum system can exist in multiple states simultaneously until an observation or measurement is made. Imagine a tiny particle, such as an electron, that doesn't have one definite position or energy level, but instead exists in a blend of possibilities at the same time. Only when you measure the electron does it choose a single state from this mixture. This idea is counterintuitive because in our everyday experience, objects are either in one state or another. This principle is central to understanding many quantum phenomena. For instance, in experiments with electrons or photons, interference patterns arise precisely because particles exist in a superposition of paths. These overlapping possibilities lead to constructive or destructive interference, creating distinct patterns on a detection screen. In more everyday terms, superposition is like having multiple potential outcomes, all coexisting until one is realized. Quantum superposition also underpins emerging technologies such as quantum computing. In a classical computer, bits can only be 0 or 1. However, quantum bits, qubits, leverage superposition, allowing them to be in a combination of both states simultaneously. This capacity dramatically increases the processing power for certain tasks, making quantum computers potentially much more efficient at solving complex problems. In essence, superposition challenges our traditional ideas of reality by showing that, at a fundamental level, nature operates with probabilities and possibilities rather than fixed certainties. It opens up a world where the boundaries between different states are blurred until a measurement forces a decision, revealing the unique and fascinating behaviour of the quantum realm. Level 7. The uncertainty principle. The uncertainty principle, formulated by Werner Heisenberg, is a key concept in quantum mechanics that limits our ability to know certain pairs of properties simultaneously. Most famously, it states that one cannot determine both the exact position and exact momentum of a particle at the same time with arbitrary precision. The more precisely one of these properties is measured, the less precisely the other can be known. This principle arises not from imperfections in our instruments, but from the fundamental nature of particles at the quantum level. In the microscopic world, particles do not have sharply defined positions and speeds as classical objects do. Instead, they are described by probabilities. The uncertainty principle reflects this inherent fuzziness. It tells us that nature itself imposes limits on how much detail we can extract. For example, when an electron is observed closely to pin down its position, its momentum becomes uncertain. This is not a flaw in measurement, but a built-in feature of quantum reality. The principle has significant implications for our understanding of atomic and subatomic systems. It suggests that there is a limit to the predictability of physical events, forcing physicists to rely on statistical methods rather than deterministic predictions. In modern applications, the uncertainty principle is essential in fields like quantum chemistry and particle physics. It affects how electrons orbit atomic nuclei and underpins many quantum phenomena. This principle also contributes to the stability of atoms as it prevents electrons from spiraling into the nucleus. Overall, the uncertainty principle is a cornerstone of quantum theory, highlighting the complex and probabilistic nature of the microscopic world. Level 8. Quantum tunneling. Quantum tunneling is a phenomenon in which particles pass through energy barriers that, according to classical physics, should be insurmountable. In classical terms, a particle needs sufficient energy to climb over a barrier. However, in the quantum world, particles can tunnel through barriers even when they do not have enough energy to overcome them directly. This effect occurs because particles at the quantum level are described by wave functions that extend into regions that would normally be forbidden. These wave functions have non-zero probabilities in areas beyond the barrier, meaning that there is a chance the particle can appear on the other side. Think of it like a ghost walking through a wall. While it might be unlikely, quantum mechanics allows for that possibility. Quantum tunneling is crucial for many natural and technological processes. In nuclear fusion, for example, protons in the sun tunnel through their mutual repulsion, allowing fusion reactions to occur at temperatures lower than would be required classically. In modern technology, tunneling is the basis for devices such as the tunnel diode, which exploits the effect to achieve very fast electronic switching. Additionally, scanning tunneling microscopes, STMs, use tunneling currents to image surfaces at the atomic scale, providing insights into material structures with extraordinary resolution. Overall, quantum tunneling reveals the non-intuitive behavior of matter at very small scales. It highlights how quantum mechanics allows particles to overcome classical barriers through probability rather than energy alone, opening the door to many technological innovations and deepening our understanding of the natural world. Level 9. Quantum entanglement. Quantum entanglement is one of the most mysterious and fascinating phenomena in quantum mechanics. When particles become entangled, their properties become linked in such a way that the state of one particle instantaneously influences the state of another, regardless of the distance between them. This interconnectedness challenges our classical ideas of separability and locality. Entangled particles share a common wave function, meaning that measurements performed on one particle immediately affect the state of its partner. For instance, if two entangled electrons are created and then separated, measuring the spin of one electron instantly determines the spin of the other, even if they are light years apart. This spooky action at a distance, as Albert Einstein famously described it, defies classical explanations and has been confirmed by numerous experiments. The phenomenon of entanglement is not just a theoretical curiosity. It plays a crucial role in emerging technologies such as quantum cryptography and quantum computing. In quantum cryptography, entangled particles are used to create secure communication channels that are theoretically immune to eavesdropping. Quantum computing leverages entanglement to perform complex calculations simultaneously, vastly increasing processing power compared to classical computers. Entanglement also raises profound philosophical questions about the nature of reality and causality. It suggests that the universe is more interconnected than our everyday experiences imply, and that the separation between objects may be less absolute than previously thought. Despite these mysteries, quantum entanglement remains one of the best verified predictions of quantum theory, continuing to inspire new research and technological advancements in the field. Level 10. Wave function. The wave function is a mathematical description that encapsulates all the information about a quantum system. It is a core concept in quantum mechanics, serving as a bridge between abstract theory and observable phenomena. Represented typically by the Greek letter psi, the wave function provides the probabilities of finding a particle in various positions and states. Unlike a classical object with a definite state, a quantum particle state is described by a wave function that spreads out over space. The square of the wave function's magnitude at a given point gives the probability of detecting the particle there. This probabilistic interpretation is central to the quantum view of nature, where certainty is replaced by likelihoods and statistical distributions. The evolution of the wave function over time is governed by the Schrödinger equation, a fundamental equation in quantum mechanics. This equation allows scientists to predict how quantum systems change and interact. The wave function can describe a wide range of systems, from electrons orbiting an atomic nucleus to complex molecules and even macroscopic systems under certain conditions. An intriguing aspect of the wave function is its collapse during measurement. When a quantum system is observed, the wave function appears to collapse from a spread out state of many possibilities into a single, definite outcome. This collapse is one of the most debated aspects of quantum theory, leading to various interpretations about the nature of reality. Overall, the wave function is a powerful tool that encapsulates the uncertainties and possibilities inherent in quantum systems. It transforms the way we understand physical phenomena by replacing deterministic trajectories with a probabilistic framework, ultimately shaping the modern view of the quantum world. Level 11, Schrödinger equation. The Schrödinger equation is a fundamental tool in quantum mechanics that describes how the state of a quantum system changes over time. Much like Newton's laws explain the motion of everyday objects, this equation governs the evolution of the wave function, a mathematical representation that encapsulates all possible states of a particle. In its time-dependent form, the Schrödinger equation incorporates both kinetic and potential energy to predict how probabilities spread out and change. A key aspect of the equation is its linearity. This means that if two solutions are valid, their sum is also a valid solution, which is essential for the idea of superposition, where a particle can exist in multiple states at once. When scientists solve the Schrödinger equation, they obtain eigenstates, which are specific, stable states of the system, associated with definite energy levels. These eigenstates form the basis for understanding phenomena like electron orbits in atoms and the behaviour of molecules. The equation also has a time-independent version that is particularly useful in systems where energy remains constant. In these cases, the wave function's form gives direct insight into the probability of finding a particle at a specific location. Over the decades, the Schrödinger equation has not only deepened our understanding of the quantum world, but also paved the way for modern technological advances, from semiconductors to lasers. Overall, the Schrödinger equation is more than just a mathematical formula. It is the bridge that connects theoretical ideas with observable quantum behaviour. Its formulation has transformed physics, enabling us to predict and manipulate the behaviour of matter at the smallest scales with unprecedented accuracy. Level 12, Schrödinger's cat. Schrödinger's cat is a famous thought experiment that challenges our intuitive grasp of quantum mechanics. Conceived by Erwin Schrödinger, the experiment involves placing a cat in a sealed box, alongside a device containing a radioactive atom, a Geiger counter, and a vial of poison. The setup is arranged so that if the atom decays, the Geiger counter triggers the release of poison, potentially killing the cat. According to quantum theory, until an observation is made, the atom exists in a superposition of decayed and undecayed states, meaning the cat is simultaneously alive and dead. This paradox highlights the puzzling nature of quantum superposition when extended to everyday objects. It questions the point at which a quantum system stops behaving in probabilistic ways and starts exhibiting a definite state, a process often linked to the act of measurement. The thought experiment does not intend to suggest that a cat can literally be alive and dead at the same time. Rather, it is designed to show that applying quantum ideas to macroscopic objects leads to seemingly absurd conclusions. Schrödinger's cat has sparked debates about the role of the observer in quantum mechanics. Interpretations such as the Copenhagen interpretation propose that the act of observation causes the collapse of the wave function into one outcome. Meanwhile, alternative views like the many worlds interpretation suggest that every possible outcome occurs in separate, branching universes. By illustrating the clash between quantum behaviour and everyday experience, Schrödinger's cat remains one of the most enduring symbols of quantum mechanics, inspiring both scientific inquiry and philosophical discussion about the nature of reality. Level 13, Quantum Measurement. Quantum measurement is the process by which a quantum system's probabilistic state becomes a definite outcome upon observation. In the quantum realm, particles do not have fixed properties until measured. Instead, they exist in a superposition of all possible states. The act of measurement causes the wave function to collapse into one specific state, though the exact mechanism behind this collapse remains one of the most debated topics in physics. Before measurement, the quantum system is described by a wave function that contains all potential outcomes and their associated probabilities. When an observer interacts with the system, whether by using an instrument or any other means, the interaction forces the system to adopt one of these outcomes. This phenomenon is not due to imperfections in measurement tools, but is intrinsic to the nature of quantum reality. The implications of quantum measurement are profound. Unlike classical measurements, which reveal properties that already exist, quantum measurements seem to create reality in the moment of observation. This has led to various interpretations of quantum mechanics. The Copenhagen interpretation suggests that measurement is a special process that brings potentiality into actuality, while other interpretations, like many worlds, propose that all outcomes occur in different branches of a continually splitting universe. In practical terms, understanding quantum measurement is crucial for developing emerging technologies such as quantum computers and quantum communication systems. These systems rely on precise control and measurement of quantum states to function effectively. As research continues, the study of quantum measurement remains a vibrant field, helping us explore the boundary between the quantum and classical worlds and challenging our conventional ideas about observation and reality. And Level 14, Eigenstates. Eigenstates are specific, stable states of a quantum system that yield definite outcomes when a measurement is made. They are solutions to the Schrödinger equation and serve as the building blocks for understanding the behavior of particles at the quantum level. When a property such as energy or momentum is measured, the system is found in one of its eigenstates, and the corresponding eigenvalue is the measured value. These states are special because they do not change when the measurement is performed. If a quantum system is in an eigenstate of a particular observable, the act of measuring that observable will always return the same result. For example, electrons in an atom occupy distinct energy levels, each of which is an eigenstate. The differences between these energy levels explain why atoms absorb or emit light at specific frequencies. Eigenstates also play a vital role in constructing more complex quantum states. Any quantum state can be expressed as a combination or superposition of eigenstates. This means that even if a system is not initially in a single eigenstate, its behavior can be understood by breaking it down into these fundamental components. The coefficients in such a combination determine the probability of finding the system in each eigenstate upon measurement. Understanding eigenstates simplifies the analysis of quantum systems. They provide a clear framework for predicting outcomes and are essential in numerous applications, from spectroscopy to the design of quantum circuits in computing. Eigenstates, with their precise and unchanging nature upon measurement, form a cornerstone of quantum theory, offering a stable foundation in a realm otherwise dominated by probabilities and uncertainty. Level 15, Quantum Decoherence. Quantum decoherence is the process by which a quantum system loses its uniquely quantum behavior due to interactions with its environment. In an isolated system, particles can exist in superpositions, where they hold multiple states simultaneously. However, when these particles interact with surrounding particles, radiation, or other environmental factors, the delicate phase relationships that enable superposition begin to break down. Decoherence does not involve a mysterious collapse of the wave function due to observation. Instead, it happens naturally as the system becomes entangled with its environment. This process transforms the coherent quantum state into an incoherent mixture of states, making the system appear classical. In practical terms, decoherence explains why we do not observe everyday objects, like chairs or cats, displaying quantum superposition, even though they are made up of quantum particles. The concept of decoherence is critical for understanding the quantum to classical transition. It shows that classical behavior emerges from quantum rules as a result of environmental interactions, not because of any special measurement process. This understanding is crucial in modern quantum technologies. For instance, quantum computers must maintain coherence among qubits to perform calculations accurately. Decoherence, which introduces errors by forcing qubits into definite states prematurely, is one of the main challenges in building reliable quantum devices. Researchers work on various techniques to minimize decoherence, such as isolating quantum systems from external influences and employing error correction protocols. By mitigating the effects of decoherence, it is possible to extend the time during which quantum behavior can be observed and utilized. Level 16. Quantum Field Theory. Quantum field theory, QFT, is a framework that unites quantum mechanics and special relativity to describe how particles and forces interact. In quantum field theory, particles are seen not as isolated objects, but as excitations in fields that fill all of space. Each particle type has its own field, and disturbances in these fields manifest as particles. For example, electrons arise from the electron field, while photons come from the electromagnetic field. In this picture, interactions occur when fields influence one another. A key tool for visualizing these interactions is the Feynman diagram, which represents particle exchanges and force mediation. These diagrams simplify complex processes by showing how particles, like ripples in a pond, interact and sometimes even create or annihilate one another. Another important aspect of QFT is its treatment of infinities that naturally appear in calculations. Through renormalization, scientists can adjust these infinite terms, leading to precise predictions that match experimental results. This success has established QFT as the backbone of the Standard Model, which explains 3 of the 4 fundamental forces in nature. QFT also redefines our understanding of empty space. The vacuum in quantum field theory is a seething background of fluctuating fields and temporary excitations. This dynamic view of the vacuum opens up the possibility of phenomena like virtual particles, which appear and vanish in brief instants. In essence, quantum field theory provides a deep and unifying language to describe the microscopic world. It explains how particles emerge, interact, and vanish, setting the stage for understanding the forces that govern the universe. As researchers continue to probe deeper, QFT remains a vibrant area of study, bridging abstract theory with the practical outcomes of high-energy experiments. Level 17. Virtual particles. Virtual particles are transient fluctuations predicted by quantum field theory. Unlike ordinary particles that we can observe directly, virtual particles exist only fleetingly and cannot be detected in isolation. They emerge from the energy inherent in quantum fields, briefly appearing as disturbances that help mediate forces between real particles. These short-lived entities arise because quantum uncertainty allows for temporary violations of energy conservation. In simple terms, for very short periods, energy fluctuations create pairs of particles that almost immediately annihilate each other. Despite their ephemeral nature, virtual particles have measurable effects. They act as the force carriers in interactions. For example, virtual photons mediate the electromagnetic force between charged particles. The influence of virtual particles is evident in several physical phenomena. One striking example is the Casimir effect, where 2 closely spaced, uncharged plates experience an attractive force due to differences in the virtual particle fluctuations between and outside the plates. Similarly, virtual particles contribute to quantum corrections in particle interactions, refining the predictions of quantum theories to match experimental results. Even though virtual particles cannot be directly observed, their role is fundamental. They ensure that forces like electromagnetism and the strong nuclear force behave as they do, underpinning the structure of matter and the behavior of energy at small scales. Their existence reinforces the idea that the quantum world is a dynamic arena where even empty space is alive with activity. In summary, virtual particles are a critical, though hidden component of the quantum universe. They exemplify how the inherent uncertainty of quantum fields gives rise to phenomena that, while not directly visible, are essential for understanding the forces that govern our world. Level 18, the vacuum state. In quantum theory, the vacuum state is far from empty. While classical physics views a vacuum as a complete void, quantum mechanics reveals it to be a dynamic backdrop filled with energy and activity. Every field that exists permeates this vacuum, even in its lowest energy configuration. The vacuum state is characterized by constant, tiny fluctuations due to the uncertainty principle. These fluctuations mean that even empty space experiences brief bursts of activity, virtual particles popping in and out of existence. This restless behavior has tangible effects. One well-known example is the Casimir effect, where the energy differences in the vacuum between two closely placed metal plates create an observable force. The concept of the vacuum state challenges our conventional idea of nothingness. Instead of a barren expanse, the vacuum is a seething, active medium that contributes to the properties of particles and forces. It sets the stage for phenomena such as spontaneous emission and influences the stability of matter. In quantum field theory, the vacuum state provides the baseline or ground state from which all excitations, particles, emerge. Furthermore, the vacuum state is pivotal in discussions about the origins of the universe. The fluctuations present in the vacuum are believed to have played a role in the early moments after the Big Bang, seeding the structure of the cosmos. Research into the vacuum continues to yield surprises, highlighting that even what appears empty holds profound complexity. Ultimately, the quantum vacuum is a rich and vibrant foundation of physical reality. It underlines the idea that nothing can be a source of energy and influence, reshaping our understanding of both microscopic phenomena and the vast universe. Level 19, spin. Spin is a fundamental quantum property, representing an intrinsic form of angular momentum that particles possess. Unlike classical spinning objects, quantum spin does not imply that a particle is physically rotating. Instead, it is an inherent characteristic that influences how particles interact with magnetic fields and other particles. Each particle has a specific spin value, typically measured in fractions of the reduced Planck constant. For example, electrons have a spin of 1/2, while photons have a spin of 1. This quantization means that a particle's spin can only adopt certain discrete values, which plays a crucial role in determining its behavior and the rules it follows. Spin is essential for explaining a variety of phenomena. In atoms, electron spin contributes to the structure of electron shells and affects how atoms bond together. The Pauli exclusion principle, which arises from the properties of spin, prevents identical fermions, particles with half-integer spin, from occupying the same quantum state simultaneously. This principle is key to understanding the arrangement of electrons in atoms and, by extension, the entire periodic table. Furthermore, spin is central to technologies such as magnetic resonance imaging, MRI. In these applications, the magnetic properties of particles are exploited to produce detailed images of the human body. Spin also underpins quantum entanglement, where the spin states of particles become linked over distances, demonstrating some of the most intriguing aspects of quantum mechanics. In summary, spin is a uniquely quantum attribute that influences both the microscopic behavior of particles and practical technologies in our macroscopic world. It is a fundamental building block of quantum theory that continues to shape our understanding of the natural world. Level 20, quantum chromodynamics. Quantum chromodynamics, QCD, is the theory that explains the strong nuclear force which binds quarks together inside protons, neutrons, and other hadrons. In QCD, quarks are the fundamental constituents of matter, and they come in different types or flavors. However, the most distinctive feature of quarks is their color charge, which is unrelated to visual color, but is a property that determines how they interact. Gluons, the carriers of the strong force, mediate the interactions between quarks. Unlike photons in electromagnetism, Gluons themselves carry color charge, which results in a highly complex network of interactions. One of the most fascinating aspects of QCD is confinement. Quarks are never found alone, but are always confined within composite particles. As quarks try to separate, the strong force does not diminish. Instead, it becomes stronger, ensuring they remain bound together. Another significant property of QCD is asymptotic freedom. At extremely high energies or very short distances, quarks behave almost as free particles, interacting only weakly with one another. This behavior has been confirmed in experiments at high-energy particle accelerators and is a vital element of modern particle physics. Quantum chromodynamics has profound implications for our understanding of matter under extreme conditions. It explains not only the structure of atomic nuclei, but also phenomena observed in high-energy collisions and the behavior of matter in neutron stars. The mathematical framework of QCD, though complex, continues to be refined through both theoretical advances and experimental evidence. In essence, quantum chromodynamics is the cornerstone of our understanding of the strong interaction, revealing how the basic constituents of matter interact and bind together. Its principles are essential to the Standard Model and remain a vibrant area of research in the quest to unravel the mysteries of the subatomic world. Level 21. Quarks. Quarks are the fundamental building blocks of matter, forming the core of protons and neutrons inside atomic nuclei. Unlike electrons, which exist independently, quarks never appear alone in nature due to a phenomenon known as confinement. Instead, they are permanently bound together by the strong nuclear force, mediated by particles called gluons. There are 6 types, or flavors of quarks: up, down, charm, strange, top, and bottom. The up and down quarks are the most common, as they make up protons and neutrons. The heavier quarks, charm, strange, top, and bottom, exist only briefly in high-energy environments, such as inside particle accelerators or during cosmic events like supernovae. Quarks also have a unique property called color charge, which is unrelated to actual colors, but is used to describe their interactions in quantum chromodynamics, QCD. There are 3 colors, red, green, and blue, and quarks combine in ways that result in a color-neutral state. For example, a proton consists of 2 up quarks and 1 down quark, with each quark carrying a different color charge that balances out. The discovery of quarks in the 1960s helped resolve mysteries about subatomic particles and led to the development of the Standard Model of particle physics. Today, experiments at facilities like the Large Hadron Collider, LHC, continue to probe quarks, shedding light on their properties and behavior under extreme conditions. Quarks are among the most essential particles in nature, forming the basis of all visible matter. Despite their tiny size, their interactions shape everything we see, from atoms to galaxies. Level 22. Gluons. Gluons are the force carriers of the strong nuclear force, the fundamental interaction responsible for holding quarks together inside protons, neutrons, and other hadrons. Just as photons mediate the electromagnetic force, gluons transmit the strong force, binding quarks so tightly that they cannot exist freely in nature. Unlike other force carriers, gluons themselves carry the color charge they mediate. This leads to a highly complex and self-interacting force field. While quarks are confined inside particles, gluons constantly exchange color charge between them, creating an incredibly strong bond. In fact, as quarks try to separate, the force between them increases, similar to a stretched rubber band. If the energy becomes too high, new quark-antiquark pairs are created rather than allowing a single quark to escape. This explains why quarks are never found in isolation. Gluons are massless, but they carry energy, making them a crucial part of the strong force. Their interactions determine the mass and structure of protons and neutrons, meaning that most of the visible mass in the universe is actually due to gluon energy rather than the quarks themselves. Understanding gluons is essential for studying high-energy physics, nuclear reactions, and even the early universe. Experiments at the LHC and quark-gluon plasma, studies in heavy ion collisions, aim to explore their properties further, helping scientists uncover more about the fundamental forces that shape our world. Level 23. Leptons. Leptons are one of the two fundamental types of particles in the Standard Model, alongside quarks. Unlike quarks, leptons do not experience the strong nuclear force, meaning they do not form composite particles like protons or neutrons. Instead, they interact via the weak nuclear force, and in some cases, the electromagnetic force. There are 6 types of leptons, grouped into 3 pairs: electron and electron neutrino, muon and muon neutrino, tau and tau neutrino. The electron is the most familiar lepton, as it is a key component of atoms. The muon and tau are heavier versions of the electron and are unstable, decaying into lighter particles in fractions of a second. Neutrinos are special leptons because they have almost no mass and no electric charge. They interact extremely weakly with matter, allowing them to pass through entire planets without being stopped. This makes them very difficult to detect, but they play an essential role in nuclear reactions, including those in the Sun. Leptons obey the Pauli exclusion principle, meaning they do not occupy the same quantum state within a system. This principle helps explain the behaviour of electrons in atoms and why matter has a structured form. Because leptons do not participate in strong interactions, their behaviour is governed primarily by the weak nuclear force and electromagnetism. Their study helps us understand particle decays, neutrino oscillations, and fundamental symmetries in physics. Level 24. The Standard Model. The Standard Model is the most successful framework for describing the fundamental particles and forces of the universe, excluding gravity. It classifies all known particles into 2 groups, fermions and bosons. The Standard Model describes 3 of the 4 fundamental forces: electromagnetic force, weak nuclear force, strong nuclear force. It does not, however, include gravity, which remains one of the biggest gaps in the theory. One of the key achievements of the Standard Model was the discovery of the Higgs boson in 2012 at the Large Hadron Collider. The Higgs boson explains why fundamental particles have mass, completing a decades-long search for the last missing piece of the model. Despite its success, the Standard Model is incomplete. It does not explain dark matter, dark energy, or the absence of antimatter in the universe. Physicists continue to search for new physics beyond the Standard Model, possibly through supersymmetry, extra dimensions, or modifications to quantum field theory. The Standard Model remains one of the most tested and confirmed theories in physics, forming the foundation of modern particle physics and shaping our understanding of the fundamental forces governing the cosmos. Level 25. Bosons. Bosons are the force-carrying particles of nature, responsible for mediating interactions between matter particles. Unlike fermions, which obey the Pauli exclusion principle and cannot occupy the same quantum state, bosons can exist in the same state, allowing them to create macroscopic quantum effects such as lasers and superconductivity. The main bosons in the Standard Model are photon, gluons, W and Z bosons, Higgs boson. Photons enable all electromagnetic interactions, from radio waves to visible light. They are massless, allowing them to travel at the speed of light. Gluons hold quarks together, making up most of the mass of protons and neutrons. Since they carry a color charge, they interact with each other, leading to the phenomenon of quark confinement. W and Z bosons govern weak nuclear interactions, which are responsible for processes like beta decay and neutrino interactions. Unlike photons, these bosons are massive, which limits the range of the weak force. The Higgs boson is unique because it gives mass to particles via the Higgs field. Without it, fundamental particles would remain massless and unable to form atoms. In addition to these, theoretical models predict other bosons, such as gravitons, which could mediate gravity if a quantum theory of gravity is ever discovered. Bosons play an essential role in shaping the universe, from holding matter together to allowing the transfer of energy and information across space. Understanding them is key to unlocking the deeper mysteries of physics. Level 26, Fermions. Fermions are the fundamental particles that make up matter. Unlike bosons, which carry forces, fermions obey the Pauli exclusion principle, meaning no two identical fermions can occupy the same quantum state simultaneously. This rule is the reason atoms have structured electron shells, allowing for the diversity of elements in the universe. There are two main types of fermions, quarks and leptons. Quarks combine to form protons and neutrons, while leptons include electrons and neutrinos. Together, they make up all known matter. Fermions have half-integer spin values, e.g. 1/2, distinguishing them from bosons, which have integer spin. This property affects how they behave under quantum statistics. Fermions follow Fermi-Dirac statistics, meaning they cannot cluster together in the same state. This is what prevents electrons from collapsing into the nucleus and enables the formation of complex chemical structures. Fermions are also subject to 3 of the 4 fundamental forces. Electromagnetic force affects charged fermions like electrons. Strong nuclear force binds quarks inside protons and neutrons. Weak nuclear force causes radioactive decay. Because they constitute everything we see, fermions are the foundation of physics. Without them, the universe would consist only of force fields with nothing to act upon. Level 27. Antimatter. Antimatter consists of particles that are nearly identical to regular matter but have opposite charge and quantum properties. For example, the antiparticle of an electron, negative charge, is the positron, positive charge. Similarly, protons have antiprotons and neutrons have antineutrons. When a particle meets its corresponding antiparticle, they annihilate in a burst of pure energy, producing photons. This reaction releases enormous amounts of energy, which is why antimatter is often depicted as a powerful energy source in science fiction. Antimatter is not just theoretical, it is produced naturally in high-energy cosmic events and in laboratories. Particle accelerators, like those at CERN, routinely create antimatter for experiments. In medical applications, positron emission tomography, PET scans, use positrons to detect metabolic activity in the human body. One of the biggest mysteries in physics is why the universe is made mostly of matter rather than a mix of matter and antimatter. The matter-antimatter asymmetry suggests that at some point, a tiny imbalance caused matter to dominate. Understanding this asymmetry is one of the biggest open questions in cosmology. While antimatter is rare in nature, studying it could unlock secrets about the early universe, fundamental forces, and even new energy sources. Level 29. Feynman diagrams. Feynman diagrams are visual representations of particle interactions in quantum field theory. Invented by Richard Feynman, these diagrams simplify complex quantum mechanical calculations by illustrating how particles interact over time. Each diagram consists of straight lines representing matter particles, e.g., electrons, quarks, wavy or curly lines representing force carriers, e.g. photons, gluons. Vertices where interactions occur. For example, in electron-electron repulsion, 2 electrons approach, exchange a virtual photon, and then move apart. This entire interaction can be drawn as a simple Feynman diagram, replacing pages of complex equations. One major advantage of Feynman diagrams is that they make calculating probabilities easier. By summing up all possible interaction pathways, physicists can predict the likelihood of certain outcomes in particle collisions. Feynman diagrams also help in understanding quantum corrections, such as vacuum fluctuations and self-energy effects. These corrections explain subtle shifts in energy levels and other real-world phenomena. Beyond QED, Feynman diagrams have been applied to nuclear physics, condensed matter physics, and even quantum gravity. They remain a fundamental tool for theoretical physicists, providing a simple yet powerful way to explore the quantum world. Level 30. Virtual photons. Virtual photons are a type of virtual particle that mediate the electromagnetic force in quantum electrodynamics, QEED. Unlike real photons, which we observe as light, virtual photons exist temporarily during particle interactions and cannot be directly detected. When two charged particles interact, they do not simply exert force on each other instantly. Instead, they exchange virtual photons, which carry the force between them. For example, when two electrons repel each other, they do so by constantly exchanging virtual photons that push them apart. Unlike real photons, virtual photons exist only for an extremely short time, as allowed by Heisenberg's uncertainty principle, can have any energy, even outside the usual energy-frequency relationship for light, never travel freely through space like ordinary photons. Virtual photons are also responsible for more complex quantum effects. They contribute to vacuum polarization, where a vacuum slightly modifies the behavior of charged particles. This effect has been observed in high-precision experiments, confirming QED's predictions. In addition to explaining fundamental forces, virtual photons are crucial in modern technology. They underlie the workings of laser physics, electromagnetic waves, and even superconductivity. Understanding them is key to unlocking new quantum technologies. Level 31. Renormalization. Renormalization is a crucial technique in quantum field theory, QFT, that allows physicists to remove infinities from calculations and make meaningful predictions. When trying to calculate interactions between particles, quantum mechanics often produces infinite values, which obviously don't make sense in a physical theory. Renormalization provides a systematic way to deal with these infinities by redefining certain physical quantities. The problem arises because, in quantum field theory, particles interact with virtual particles that appear and disappear due to quantum fluctuations. These virtual particles contribute to energy corrections, sometimes leading to infinite values in equations. Renormalization introduces a cutoff scale, allowing physicists to ignore contributions beyond a certain limit and absorb infinities into measurable parameters such as charge and mass. One famous success of renormalization is in quantum electrodynamics, QED. Without renormalization, calculations involving electron interactions would yield meaningless infinities. However, through this technique, QED makes precise predictions, matching experimental results to over 10 decimal places. Renormalization is also essential in quantum chromodynamics, QCD, and the Standard Model, helping refine our understanding of fundamental forces. Without it, modern physics would be filled with impossible infinities, making real-world predictions impossible. Level 32. Gauge symmetry. Gauge symmetry is a fundamental principle in physics that explains how forces arise from symmetries in nature. It is the mathematical backbone of the Standard Model, describing how fundamental particles interact with force carriers like photons, gluons, and WZ bosons. A gauge transformation is a small change in a field that does not alter the physical laws governing it. In electromagnetism, for example, changing the phase of an electric field at every point in space does not affect the fundamental equations. This symmetry leads directly to the existence of photons. Similarly, in the strong and weak nuclear forces, gauge symmetry dictates the presence of gluons and WZ bosons. Gauge symmetry is why forces exist. In quantum mechanics, the requirement that physical laws remain unchanged under certain transformations forces the introduction of force-carrying particles. This elegant principle allows physicists to unify interactions and predict new particles before they are even discovered. Beyond particle physics, gauge symmetry has implications in condensed matter physics, superconductivity, and even attempts at quantum gravity. Understanding these symmetries continues to drive theoretical research as physicists search for a grand unified theory that combines all fundamental forces, including gravity. Level 33. Spontaneous symmetry. Breaking. Spontaneous symmetry breaking, SSB, occurs when a system that is initially symmetric naturally settles into a state that lacks that symmetry. This process is crucial in explaining why certain fundamental forces behave the way they do. A common analogy is a pencil balanced on its tip. In theory, it can fall in any direction, but when it tips over, it chooses one particular direction, breaking the original symmetry of the system. In particle physics, SSB plays a key role in the Higgs mechanism, which explains how particles acquire mass. The equations governing the weak nuclear force originally suggest that W and Z bosons should be massless, like photons. However, they spontaneously acquire mass through interactions with the Higgs field. SSB is also observed in materials like magnets. At high temperatures, atoms in a magnet are randomly oriented, maintaining rotational symmetry. But as the temperature drops, the system chooses a particular magnetic direction, breaking the symmetry. This is similar to how the early universe transitioned from a high-energy symmetric state to the state we observe today. The concept of SSB extends to cosmology, explaining early universe phase transitions, inflation, and even dark energy. It is a powerful idea that helps describe the formation of structure in the universe, from fundamental particles to galaxies. Level 34. The Higgs mechanism. The Higgs mechanism is the process that gives fundamental particles their mass through interactions with the Higgs field. Without this mechanism, elementary particles like quarks and electrons would be massless, making atoms and life itself impossible. The idea is based on the presence of an invisible field, the Higgs field, that permeates the entire universe. When certain particles interact with this field, they gain resistance to movement, which we perceive as mass. Particles that interact strongly with the Higgs field become heavier, while those that interact weakly remain light. This mechanism was introduced to solve a problem in the Standard Model. The weak nuclear force requires W and Z bosons, but they must be massive to explain weak interactions. Initially, equations suggested that they should be massless, just like photons. However, the Higgs mechanism breaks the symmetry of the equations, allowing W and Z bosons to acquire mass while leaving the photon massless. In 2012, the Higgs boson was discovered at the Large Hadron Collider, providing experimental confirmation of the Higgs mechanism. This discovery was one of the most significant breakthroughs in modern physics, confirming a theory that had been proposed nearly 50 years earlier. The Higgs mechanism is now central to our understanding of particle physics. It helps explain why fundamental forces behave differently and offers clues about physics beyond the Standard Model, including potential links to dark matter and extra dimensions. Level 35. Higgs boson. The Higgs boson is a fundamental particle that confirms the existence of the Higgs field, which gives mass to other particles. It was first proposed in the 1960s by Peter Higgs and other physicists, but it remained undetected for decades due to its extremely high mass and elusive nature. Unlike other fundamental particles, the Higgs boson does not mediate a force. Instead, it serves as evidence that the Higgs field exists. When particles move through this field, they acquire mass, much like a person wading through water experiences resistance. The discovery of the Higgs boson at CERN's Large Hadron Collider, LHC, in 2012 was a monumental achievement. It was found through its decay signatures as it quickly breaks down into other particles. This discovery confirmed a major missing piece of the Standard Model and earned the 2013 Nobel Prize in Physics for François Englert and Peter Higgs. The Higgs boson has a mass of about 125 GeV, giga-electron volts, making it much heavier than a proton. Its interactions with other particles vary depending on their mass. Heavier particles interact more strongly, while lighter ones interact less. Beyond confirming the Standard Model, studying the Higgs boson offers insight into physics beyond the Standard Model. Some theories suggest the Higgs boson could have connections to dark matter, extra dimensions, or even the fate of the universe. The Higgs field might also play a role in cosmic inflation, the rapid expansion of the early universe. Today, experiments continue to analyze the Higgs boson's properties to uncover deeper insights into nature's fundamental forces. It remains one of the most exciting frontiers in particle physics, holding the potential for groundbreaking discoveries about the universe. Level 36. Quantum gravity. Quantum gravity is the ongoing attempt to unify general relativity, which describes gravity at cosmic scales, with quantum mechanics, which governs the microscopic world. Currently, gravity is the only fundamental force not described by quantum theory, making it a major gap in our understanding of the universe. Einstein's theory of general relativity describes gravity as the curvature of spacetime caused by mass and energy. This model works extremely well for large objects like planets, stars, and black holes. However, when trying to apply general relativity to extremely small scales, such as inside black holes or at the Big Bang, the equations break down, producing infinite values. This suggests that a deeper, quantum-based theory of gravity is needed. Several approaches to quantum gravity have been proposed. String theory suggests that fundamental particles are not point-like, but tiny vibrating strings whose interactions determine the nature of forces, including gravity. Loop quantum gravity, LQG, attempts to quantize spacetime itself, proposing that space is made of discrete loops rather than being continuous. Other theories such as causal dynamical triangulation, CDT, and emergent gravity offer alternative ways to explain gravity's quantum nature. Solving quantum gravity would help us understand the extreme physics of black holes, the early universe, and even dark energy. However, due to the lack of experimental evidence and the difficulty of testing these ideas, quantum gravity remains one of the biggest unsolved problems in physics. Level 37. String theory. String theory proposes that all fundamental particles are not zero-dimensional points, but rather tiny vibrating strings. The vibration patterns of these strings determine the properties of particles, such as mass and charge. A key feature of string theory is that it naturally includes gravity, something missing in other quantum field theories. It does this by predicting a massless particle called the graviton, which would be the quantum carrier of gravity. One of the most striking implications of string theory is the need for extra dimensions. Our universe appears to have 3 spatial dimensions and 1 time dimension, but string theory suggests that there are at least 10 or 11 dimensions. These extra dimensions are thought to be curled up at microscopic scales, making them difficult to detect. Another major concept in string theory is brane worlds, where our universe could be a 3-dimensional brane floating in a higher dimensional space. This could explain some mysteries, such as why gravity appears so weak compared to other fundamental forces. Although string theory is mathematically elegant and has influenced many areas of physics, it lacks direct experimental evidence. Critics argue that it is not falsifiable, meaning there is no clear way to prove or disprove it. Nonetheless, it remains one of the most ambitious attempts to unify quantum mechanics and gravity. Level 38. Loop quantum gravity, LQG. Loop quantum gravity, LQG, is an alternative approach to quantum gravity that suggests that spacetime itself is quantized. Instead of treating space as a continuous fabric, LQG proposes that space is made up of tiny, discrete loops. In this model, space is composed of spin networks, which are webs of quantum states that evolve over time. These networks form a fine-grained, discrete structure at the Planck scale, around 10 to the negative 35th power meters, meaning that space is fundamentally pixelated rather than smooth. One of the most important predictions of LQG is that black hole singularities disappear. Instead of an infinitely dense point at the center of a black hole, LQG suggests that quantum effects create a bounce, preventing the complete collapse of matter. This also has implications for the Big Bang, suggesting that the universe did not emerge from a singularity, but from a previous contracting phase. often referred to as the Big Bounce. Unlike string theory, which relies on extra dimensions, LQG sticks to the known four-dimensional spacetime. However, LQG has not yet been experimentally tested, and it remains an active area of research in the search for a complete theory of quantum gravity. Level 39. Multiverse Hypothesis. The multiverse hypothesis suggests that our universe is just one of many universes, each with its own laws of physics, constants, and even different types of matter and energy. This idea arises from multiple branches of physics, quantum mechanics. In the many worlds interpretation, every quantum event splits reality into multiple parallel universes where different outcomes occur. Cosmic inflation. Some versions of inflationary cosmology propose that new universes are constantly forming, leading to an infinitely expanding multiverse. String theory. The landscape of string theory suggests that different regions of space might settle into different vacuum states, each forming a separate universe. One major question is whether we can ever test the multiverse hypothesis. Since other universes may be completely disconnected from ours, it is unclear if their existence can be experimentally confirmed. However, some physicists speculate that subtle effects, such as collisions between bubble universes, might leave detectable traces in the cosmic microwave background. The multiverse concept also raises deep philosophical questions. If there are infinite universes, does every possible version of reality exist somewhere? Could there be another version of you making different choices? While intriguing, the multiverse remains highly speculative and is one of the biggest open questions in modern physics. Level 40. Quantum entropy. Entropy is a measure of disorder or uncertainty in a system. In classical physics, entropy describes the tendency of systems to move from order to disorder, such as ice melting into water. In quantum mechanics, quantum entropy is used to describe uncertainty in quantum states. One key concept in quantum entropy is the von Neumann entropy, which quantifies how much information is contained in a quantum system. A pure quantum state has zero entropy, meaning it is fully determined. However, when a system becomes entangled, its entropy increases because measuring one part of the system does not fully determine the whole. Quantum entropy also plays a crucial role in black hole thermodynamics. According to Stephen Hawking, black holes emit radiation, Hawking radiation, and gradually lose mass over time. This raises the black hole information paradox. What happens to the information that falls into a black hole? If black holes evaporate completely, does the information disappear, violating fundamental quantum principles? One possible resolution is that information is encoded in the Hawking radiation emitted by the black hole, but this remains an open question in physics. Some theories suggest that information is stored on the black hole's event horizon, an idea known as the holographic principle. Quantum entropy is also vital in quantum computing and quantum cryptography. Understanding how information behaves in quantum systems is essential for building secure communication networks and developing more powerful computing algorithms. Level 41. Decoherence time. Decoherence time refers to how long a quantum system can maintain its coherence, or quantum behavior, before interactions with the environment cause it to behave classically. In simple terms, it is the time window in which quantum superposition and entanglement can exist before being disrupted. In an ideal quantum system, particles can exist in multiple states at once, superposition, and entangled particles remain correlated across distances. However, when these systems interact with their surroundings, such as air molecules, electromagnetic fields, or even measurement devices, their quantum properties leak into the environment, effectively destroying the quantum state. This process is called quantum decoherence. Decoherence time is extremely short in most macroscopic systems, which is why we don't see quantum effects like superposition in everyday life. However, in controlled environments like ultra-cold quantum computers or isolated atomic systems, coherence can be maintained for longer periods. Quantum technologies such as quantum computers and quantum cryptography rely on maximizing decoherence time. Scientists work on methods like error correction and isolation techniques to extend coherence and maintain fragile quantum states. Understanding and controlling decoherence time is one of the biggest challenges in quantum mechanics, directly impacting the feasibility of quantum computing, precision measurements, and fundamental research into the quantum classical boundary. Level 42. Density matrix. A density matrix is a mathematical tool used in quantum mechanics to describe quantum systems, especially when there is uncertainty or partial knowledge about the system's state. Unlike the wave function, which describes a quantum system in complete detail, the density matrix can represent both pure and mixed quantum states. Pure states. The system is in a well-defined quantum state, like a single electron in superposition. These states can be described by a standard wave function. Mixed states. The system is in a combination of multiple possible quantum states, often due to decoherence or interactions with the environment. In these cases, a wave function alone is not enough, and a density matrix provides a more general description. The density matrix is particularly useful in quantum statistical mechanics, where systems are in thermal equilibrium, quantum computing, where it helps describe qubit operations, especially when errors and noise are present, quantum optics, where light fields can be in complex states of superposition and entanglement. The ability to describe both isolated quantum systems and those affected by their environment makes the density matrix a powerful tool for understanding real-world quantum behavior. Level 43. Bell's theorem. Bell's theorem is one of the most important results in quantum mechanics, proving that no local hidden variable theory can fully explain quantum entanglement. In simple terms, it shows that the strange correlations observed in entangled particles cannot be explained by any classical model where information is limited by the speed of light. John Bell formulated this theorem in 1964, providing a way to test whether quantum mechanics or classical physics correctly describes reality. His idea was to compare the statistical outcomes of measurements on entangled particles with what would be expected if the particles had pre-existing, hidden properties. Bell's theorem leads to an experimental test called Bell's inequality. If classical physics is correct, the measured correlations between entangled particles should obey Bell's inequality. If quantum mechanics is correct, then entangled particles should violate Bell's inequality, showing correlations stronger than what classical physics predicts. Many experiments, including those by Alain Aspect in the 1980s, and more recent tests in 2015, have confirmed violations of Bell's inequality, proving that quantum mechanics is correct. This means that reality is either fundamentally non-local or does not have predefined properties before measurement. Bell's theorem has deep implications for quantum information, cryptography, and the nature of reality itself, challenging classical notions of how the universe works. Level 44. Non-locality. Non-locality is one of the strangest and most debated features of quantum mechanics. It refers to the idea that entangled particles can instantaneously influence each other even when separated by vast distances. This challenges our classical understanding of cause and effect and suggests that quantum information is not limited by the speed of light. The existence of non-locality was confirmed by Bell's theorem and its experimental tests, which showed that quantum correlations cannot be explained by local hidden variables. When two entangled particles are measured, the result of one measurement instantly determines the outcome of the other, no matter how far apart they are. Despite its bizarre nature, non-locality does not violate relativity because it cannot be used to transmit information faster than light. Instead, it suggests that reality, at the quantum level, is interconnected in a way that defies classical intuition. Non-locality plays a crucial role in quantum technologies. Quantum teleportation relies on non-local correlations to transfer quantum states. Quantum cryptography ensures secure communication by detecting any eavesdropping attempts. Quantum computing exploits non-local interactions for faster information processing. Non-locality remains one of the biggest mysteries in physics, raising deep questions about the fundamental nature of space, time, and causality. Level 45. Quantum cryptography. Quantum cryptography is a revolutionary approach to secure communication that relies on the principles of quantum mechanics to prevent eavesdropping. Unlike classical encryption, which depends on mathematical complexity, quantum cryptography is physically unbreakable due to the fundamental laws of quantum mechanics. The most famous quantum cryptographic protocol is quantum key distribution, QKD. Specifically, the BB84 protocol, developed by Charles Bennett and Gilles Brassard in 1984. It works as follows. A sender, Alice, transmits a series of quantum states, photons, to a receiver, Bob. The quantum states represent a secret key that can be used for encryption. If an eavesdropper, Eve, tries to intercept the photons, quantum mechanics ensures that the measurement disturbs the system, revealing her presence. Alice and Bob can detect any interception and discard the compromised key. This method ensures perfect security, as any attempt to measure or copy the key inevitably alters it. Unlike traditional encryption, which can be broken with enough computational power, QKD remains secure, even against future quantum computers. Practical implementations of quantum cryptography are already in use. China launched the Mycius satellite, the world's first quantum communication satellite, to enable secure long-distance quantum communication. Several companies and governments are developing quantum-secured networks for financial transactions and military communications. Beyond QKD, researchers are also exploring quantum-resistant cryptography, which aims to develop classical encryption methods that cannot be broken by quantum computers. Quantum cryptography represents the next era of cybersecurity, leveraging the unique properties of quantum mechanics to ensure unbreakable security in the digital age. Level 46. Qubits. Qubits, or quantum bits, are the basic units of information in quantum computing. Unlike classical bits, which can only be 0 or 1, qubits can be in both 0 and 1 at the same time due to superposition. This allows quantum computers to perform multiple calculations simultaneously. Qubits also have entanglement, meaning that when 2 or more qubits are linked, the state of one qubit instantly affects the state of the others, no matter how far apart they are. This enables faster and more efficient processing compared to classical computers. Different physical systems can be used to create qubits, such as superconducting circuits, trapped ions, and photons. However, qubits are extremely sensitive to their environment, which makes maintaining their quantum state, coherence, a major challenge in quantum computing. Researchers are working on ways to improve qubit stability and error correction to make quantum computers more practical. Level 47. Quantum computing. Quantum computing is a new way of processing information using the principles of quantum mechanics. Unlike traditional computers, which process information using bits, zeros and ones, quantum computers use qubits, which can exist in multiple states at once. Because of superposition, quantum computers can solve complex problems much faster than classical computers. Entanglement also plays a key role, allowing qubits to work together in a way that classical bits cannot. Quantum computers have the potential to revolutionize fields like cryptography, drug discovery, and artificial intelligence. For example, they could quickly break encryption codes that would take traditional computers millions of years to crack. However, quantum computers are still in the early stages of development. One major challenge is error correction, as quantum systems are extremely fragile and easily disrupted by their surroundings. Companies like Google, IBM, and Microsoft are racing to build more stable quantum computers, with the goal of achieving quantum supremacy, where quantum computers outperform classical computers in practical tasks. Level 48. Quantum algorithms. Quantum algorithms are specialized methods designed to take advantage of quantum computing's unique properties. These algorithms use superposition and entanglement to solve problems much faster than traditional methods. Some of the most famous quantum algorithms include Shor's algorithm, used for breaking encryption by factoring large numbers exponentially faster than classical computers. Grover's algorithm speeds up searching large databases, making it much faster than classical search methods. Quantum Fourier transform, essential for many quantum algorithms, including signal processing and cryptography. These algorithms are still being refined, but they hold huge potential for revolutionizing industries like security, optimization, and artificial intelligence. The challenge is that today's quantum computers are still too small and error-prone to fully use these algorithms at scale. As hardware improves, quantum algorithms will become increasingly practical. Level 49. Quantum error correction. Quantum error correction is a crucial technique used to protect quantum information from errors caused by interference from the environment. Unlike classical bits, which can be stored and copied easily, qubits are extremely fragile, and even the smallest disturbance can cause them to lose information. Because quantum mechanics does not allow copying qubits directly, traditional error correction methods do not work. Instead, quantum error correction relies on encoding information into multiple entangled qubits in a way that allows errors to be detected and fixed without destroying the quantum state. Some of the most well-known error correction codes include Shor code, the first quantum error correction method, which protects a qubit by spreading its information across multiple qubits. Surface codes, a more advanced method used in modern quantum computers to detect and correct errors efficiently. Quantum error correction is one of the biggest hurdles in building large-scale quantum computers. Without it, quantum computations would be too unreliable for practical use. Companies like Google, IBM, and Microsoft are actively researching ways to improve error correction, bringing us closer to practical quantum computing. Level 50. Topological quantum states. Topological quantum states are special quantum states that store information in a way that makes them highly resistant to errors. These states are used in topological quantum computing, a type of quantum computing designed to be much more stable than other methods. In traditional quantum computing, qubits are very delicate and easily disturbed. However, in topological quantum computing, information is stored in the braiding of particles called anyons. These particles follow strange quantum rules that make their states naturally protected from environmental noise, reducing errors. This approach is being developed by Microsoft and other research groups because it could lead to more reliable quantum computers. However, topological quantum states are extremely difficult to create and control. Scientists are still working on proving their practical use, but if successful, they could solve one of the biggest problems in quantum computing, error correction, without needing as much complex error correction coding. Topological quantum states represent one of the most exciting frontiers in quantum physics and could be the key to unlocking large-scale, practical quantum computing in the future. Level 51. Berry phase. The Berry phase is a strange quantum effect that occurs when a quantum system slowly evolves in a closed loop. Unlike ordinary phase shifts, which arise from time evolution, the Berry phase is purely geometric, meaning it depends on the path a system takes rather than the time it takes to get there. Imagine walking on a sphere and returning to your starting point after taking a curved path. Even though you're back at the same place, your orientation might be different depending on the path you took. Similarly, in quantum mechanics, the Berry phase represents a kind of memory of the path a system has travelled through quantum space. This effect is crucial in quantum computing condensed matter physics, and optics. In particular, it plays a role in the quantum Hall effect, topological insulators, and even the behavior of electrons in magnetic fields. The Berry phase also appears in adiabatic quantum computing, where quantum systems are evolved slowly to solve problems. Understanding it helps physicists develop better quantum devices and explore exotic quantum states. Level 52. Aharonov-Bohm effect. The Aharonov-Bohm effect is one of the most fascinating demonstrations of quantum mechanics, showing that particles can be affected by electromagnetic potentials even in regions where there is no force acting on them. In classical physics, charged particles like electrons only respond to direct forces, such as electric and magnetic fields. However, in quantum mechanics, the mere presence of a potential field, like a magnetic vector potential, can change the phase of an electron's wave function, even if the electron never passes through the actual field. A classic experiment to demonstrate this involves sending electrons through a split path around a magnetically shielded region. Even though there is no magnetic field in the electron's path, their wave functions interfere in a way that reveals a phase shift, proving that quantum particles sense the field indirectly. This effect has deep implications for gauge theories, quantum field theory, and the nature of reality. It also has applications in nanoelectronics, quantum sensors, and precision measurement devices. Level 53. Quantum optics. Quantum optics is the study of how light interacts with quantum systems. Unlike classical optics, which treats light as a continuous wave, quantum optics explores how individual photons behave and how they can be manipulated at the quantum level. Some of the key topics in quantum optics include single photon sources, creating and detecting individual photons for quantum communication, entangled photons using light to generate quantum entanglement for cryptography and computing, lasers and coherence, understanding how light maintains phase relationships in quantum states. Quantum optics plays a huge role in quantum communication, quantum computing, and precision metrology. Technologies like quantum key distribution, QKD, used for secure communication, rely on the principles of quantum optics to prevent eavesdropping. Additionally, ultra-cold atom experiments and optical lattices use quantum optics to study new states of matter, paving the way for advances in both fundamental physics and real-world technology. Level 54. Coherent states. A coherent state is a special quantum state where a system behaves as closely as possible to a classical wave. These states were first introduced in the context of quantum optics to describe laser light, which exhibits nearly perfect coherence. In a coherent state, quantum uncertainties in position and momentum, or other conjugate variables like phase and amplitude, are distributed in a way that minimizes disturbances. This means coherent states are the closest quantum equivalent to classical waves, making them very useful in fields like laser physics. Coherent states describe the pure, stable light produced by lasers. Quantum communication. They are used in quantum encryption and optical networks. Quantum computing. Some quantum processors use coherent states for error-resistant calculations. Coherent states also provide a deeper understanding of quantum harmonic oscillators, which are used in many areas of physics, from particle theory to quantum mechanics. They serve as a bridge between classical and quantum physics, helping scientists develop new technologies that harness both worlds. Level 55. Squeezed states. Squeezed states are quantum states where the uncertainty in one property, such as position or momentum, is reduced below the usual quantum limit, at the cost of increasing uncertainty in another property. This allows quantum systems to perform better than classical limits in precision measurements. For example, in quantum optics, squeezed light can be used to improve the sensitivity of interferometers, like those used in gravitational wave detection, such as LIGO. By reducing the noise in one part of the signal, while allowing more noise in another, squeezed states help detect incredibly faint cosmic ripples from distant black hole mergers. Squeezed states are also useful in quantum metrology, making ultra-precise measurements beyond classical limitations. Quantum computing, enhancing the stability of qubits. Quantum cryptography, improving secure communication by reducing noise in optical signals. By manipulating squeezed states, scientists can push the boundaries of precision measurement and quantum technology, leading to breakthroughs in fields as diverse as astronomy, medicine, and secure data transmission. Level 56. Quantum metrology. Quantum metrology is the science of using quantum effects to make measurements more precise than classical limits allow. Traditional measurement techniques are limited by the Heisenberg uncertainty principle, but quantum mechanics provides ways to push beyond these limits. Some key quantum techniques used in metrology include squeezed states. These reduce uncertainty in one variable, like position or phase, while increasing it in another, improving measurement accuracy. Quantum entanglement. Correlated quantum states allow for more precise measurements, such as in atomic clocks and gravitational wave detectors. Interferometry. Devices like LIGO, which detects gravitational waves, rely on quantum metrology to measure tiny distortions in spacetime. Quantum metrology has applications in navigation, timekeeping, and fundamental physics research. For example, atomic clocks based on quantum principles are so precise that they can detect tiny changes in gravity due to Earth's mass variations. These clocks are essential for GPS systems, telecommunications, and scientific experiments that test the nature of time and relativity. In the future, advances in quantum metrology could lead to better sensors, ultra-precise microscopes, and even new ways to detect dark matter or quantum gravitational effects. Level 57. Casimir effect. The Casimir effect is a strange quantum phenomenon where two uncharged parallel metal plates placed close together in a vacuum experience an attractive force. This happens due to quantum fluctuations in empty space. In classical physics, a vacuum is empty. But in quantum mechanics, the vacuum is filled with virtual particles that constantly pop in and out of existence. These fluctuations create tiny forces that push objects together or apart. The Casimir effect is important because it proves that empty space isn't truly empty. It's an active field of quantum energy. It has been measured in laboratory experiments and plays a role in nanotechnology, condensed matter physics, and even theories of dark energy. In practical applications, the Casimir effect is considered in the design of nano-electromechanical systems, NEMS, where tiny components can be affected by quantum vacuum forces. Scientists also explore ways to reverse or control the effect, which could lead to new types of frictionless surfaces or energy harvesting devices. Level 58. Zero-point energy. Zero-point energy is the lowest possible energy a quantum system can have. Even in a perfect vacuum at absolute zero, quantum fields still have fluctuations, meaning there is always some residual energy present. This idea comes from Heisenberg's uncertainty principle, which states that it's impossible for a system to have exactly zero energy, because that would mean both its energy and momentum are precisely known, violating quantum rules. Zero-point energy has big implications for physics. In cosmology, it could help explain dark energy, which is causing the universe to expand at an accelerating rate. In quantum field theory, it contributes to phenomena like the Casimir effect and spontaneous particle creation. Some theories speculate that if we could harness zero-point energy, we could develop new energy sources or advanced propulsion systems, though no practical method has been found yet. While it remains a theoretical concept for now, zero-point energy continues to be a topic of deep interest in both fundamental physics and speculative future technologies. Level 59. Bose-Einstein condensate. A Bose-Einstein condensate, BEC, is a state of matter that occurs when a group of bosons, particles with integer spin, are cooled to extremely low temperatures, near absolute zero. At this point, the bosons collapse into the same quantum state, behaving as a single superparticle. In a BEC, quantum effects become visible at a macroscopic scale. Instead of behaving as individual particles, the atoms act collectively as one unified quantum system. This was first predicted by Albert Einstein and Satyendra Bose in the 1920s and was experimentally confirmed in 1995 by Eric Cornell and Carl Wieman, who won a Nobel Prize for the discovery. Key properties of BECs include superfluidity. BECs can flow without friction, similar to how liquid helium behaves at low temperatures. Quantum coherence. All the atoms behave in a synchronized manner, like a giant wave. Slow light effects. BECs can slow down or even stop light, which has potential applications in quantum computing and information storage. BECs are used in precision measurements, quantum simulations, and fundamental tests of quantum mechanics. Scientists are exploring their use in quantum computing, ultra-sensitive sensors, and even space experiments to study gravity in new ways. Level 60. Fermionic condensate. A fermionic condensate is similar to a Bose-Einstein condensate, but instead of bosons, it is made of fermions, particles with half-integer spin, like electrons and neutrons. Unlike bosons, fermions cannot occupy the same quantum state, due to the Pauli exclusion principle. This makes creating a fermionic condensate much more challenging. To form a fermionic condensate, atoms are cooled to ultra-low temperatures, where they begin to pair up in ways similar to how electrons form Cooper pairs in superconductors. This pairing allows them to behave collectively, similar to a BEC. Key properties of fermionic condensates. Superfluidity. Just like BECs, fermionic condensates can flow without friction. Quantum pairing. Particles form weakly bound pairs, similar to the behavior in superconductors. Bridge between BEC and superconductivity. Fermionic condensates help scientists understand the transition between BECs and the mechanisms behind superconductivity. Fermionic condensates could lead to advances in high-temperature superconductors, which would revolutionize energy transmission, quantum computing, and material science. Level 61. Superfluidity. Superfluidity is a quantum phenomenon where a liquid flows without any viscosity or resistance. This means a superfluid can move through narrow spaces, climb walls, or even remain motionless when placed in a rotating container. Superfluidity was first observed in liquid helium when it was cooled to temperatures close to absolute zero. Unlike normal fluids, superfluids don't lose energy to friction, allowing them to flow indefinitely. Key properties of superfluids. Zero viscosity. A superfluid can move without losing energy. Quantum vortices. When superfluids rotate, they form tiny, stable whirlpools rather than spinning like a normal liquid. Frictionless flow. Superfluid helium can move through tiny cracks and even climb walls. Superfluidity is important in quantum mechanics, condensed matter physics, and astrophysics. Some theories suggest that the interiors of neutron stars could be superfluid, affecting how these dead stars rotate and emit radiation. In practical applications, superfluidity is being explored for quantum computing, precision sensors, and advanced cooling systems. Level 62. Superconductivity. Superconductivity is the ability of certain materials to conduct electricity with zero resistance when cooled below a critical temperature. This means that an electric current can flow indefinitely without losing energy. Superconductors also exhibit the Meissner effect, where they completely expel magnetic fields, allowing them to levitate magnets. This is the basis for magnetic levitation, maglev trains, and other futuristic technologies. Types of superconductors. Low-temperature superconductors. Require extreme cooling, often with liquid helium. High-temperature superconductors. work at more practical temperatures and are being developed for real-world applications. Applications of superconductivity include maglev trains, using superconducting magnets to create frictionless transportation, MRI machines. Superconducting coils generate strong magnetic fields for medical imaging. Quantum computers. Many quantum systems, like those developed by IBM and Google, rely on superconducting qubits. Scientists are still searching for room temperature superconductors, which would revolutionize energy transmission, electronics, and transportation. Level 63. Quantum phase transitions. In classical physics, phase transitions occur when a material changes state, like ice melting into water. Quantum phase transitions, however, happen at absolute zero and are driven by quantum fluctuations instead of temperature. These transitions occur when an external parameter, such as magnetic field, pressure, or electron density, is varied, causing a sudden change in the material's properties. Unlike classical phase transitions, which depend on thermal energy, quantum phase transitions involve entanglement and quantum correlations. Examples of quantum phase transitions include superfluid to insulator transition. In ultracold atoms, adjusting the interaction strength can turn a superfluid into an insulator. Magnetic phase transitions. Some materials shift from magnetic to non-magnetic states purely due to quantum effects. Topological phase transitions. These involve exotic states of matter, like quantum Hall states, and topological insulators. Quantum phase transitions are important for developing new quantum materials, superconductors, and advanced quantum technologies. Understanding them helps physicists explore new states of matter that could lead to breakthroughs in computing and energy storage. Level 64. Landau levels. Landau levels describe the quantized energy states of charged particles in a magnetic field. When an electron moves through a magnetic field, it doesn't move freely. Instead, it forms discrete energy levels due to quantum effects. This concept was first introduced by Lev Landau, a Soviet physicist, and it is crucial for understanding electron behavior in magnetic fields. Key features of Landau levels: cyclotron motion. Electrons move in circular orbits, constrained by the magnetic field. Energy quantization. Instead of a continuous range, electrons can only occupy specific energy levels. Quantum Hall effect. Landau levels play a key role in this effect, where electrical resistance becomes quantized in a magnetic field. Landau levels are important in semiconductor physics, quantum Hall systems, and the study of topological materials. They also provide insights into high-mobility electron systems, which are essential for developing ultra-fast transistors and quantum devices. Level 65. Quantum Hall effect. The quantum Hall effect, QHE, is a fascinating quantum phenomenon where the electrical resistance of a two-dimensional electron system becomes quantized when exposed to a strong magnetic field. This means that the resistance only takes on specific, fixed values, rather than changing smoothly. The effect comes in two main forms. Integer, quantum Hall effect. The resistance is quantized in whole number steps due to Landau levels. Fractional quantum Hall effect, more exotic, where electrons form strange quasi-particles that carry fractional charge. Why is this important? The quantum Hall effect provided experimental proof of topological physics, leading to breakthroughs in understanding topological insulators and exotic quantum states. It is used to define the standard of electrical resistance, ensuring precise measurements in physics and engineering. It plays a role in developing future quantum devices and fault-tolerant quantum computers. The discovery of the quantum Hall effect was so groundbreaking that it led to two separate Nobel Prizes, one in 1985 for the integer effect, and another in 1998 for the fractional effect. This effect is one of the best demonstrations of how quantum mechanics and topology work together to create new and surprising physical phenomena. Level 66. Fractional quantum Hall effect. The fractional quantum Hall effect, FQHE, is an extension of the integer quantum Hall effect, but with a fascinating twist. It involves the emergence of quasi-particles that have fractional electric charge. This is one of the most striking examples of how strong interactions between electrons can create entirely new types of quantum states. In the traditional quantum Hall effect, electrons in a two-dimensional material form distinct energy levels, called Landau levels, under a strong magnetic field. However, when the system is cooled to extremely low temperatures and the electron density is adjusted, something strange happens. The electrical resistance starts behaving in fractional steps, such as 1/3 or 1/5 of expected values. This discovery, made by Daniel Tsui and Horst Sturmer in 1982, led to the realization that electrons in this system do not behave as individual particles. Instead, they collectively form a new type of quantum state, where the electron fluid behaves as though it contains particles with fractional charge. Why is this important? The FQHE introduced the concept of anyons, particles that are neither fermions nor bosons, but something in between. These anyons exhibit topological order, meaning their properties depend on the system's global structure rather than local details. This makes FQHE states promising for topological quantum computing, where quantum information could be stored in a way that is naturally resistant to errors. FQHE was so groundbreaking that it earned the 1998 Nobel Prize in Physics and remains a key topic in condensed matter physics, with potential applications in fault-tolerant quantum computing. Level 67. Anderson localization. Anderson localization is a quantum phenomenon where waves, such as electrons, light, or even sound, become trapped in a disordered system, preventing them from spreading freely. In a perfect crystal, electrons move smoothly, like light through glass. But in materials with random impurities or structural disorder, electron movement can be disrupted so much that they become localized, meaning they stop conducting electricity efficiently. This was first proposed by Philip Anderson in 1958, who later won the Nobel Prize in Physics in 1977 for this discovery. Key features of Anderson localization: happens in disordered materials where randomness blocks wave-like motion, applies to both electrons and photons, affecting conductivity and optical properties, leads to insulating behavior, explaining why some materials fail to conduct electricity even when they should. This effect is important in semiconductor physics, where understanding electron mobility is crucial for designing transistors and microchips. Optical materials, where localized light waves could lead to new types of lasers or energy-efficient LEDs. Quantum information, where controlling localization could be useful for protecting quantum states from decoherence. Anderson localization shows how randomness in a system can fundamentally alter its physical behavior, which has major implications for electronics, materials science, and quantum technology. Level 68. Many-body localization. Many-body localization, MBL, is a quantum extension of Anderson localization, where not just single particles, but entire interacting systems become localized due to disorder. Unlike Anderson localization, which happens in non-interacting systems, MBL occurs even when particles strongly interact with each other. In classical physics, interacting systems eventually reach thermal equilibrium, meaning they spread energy evenly over time. But in MBL systems, interactions fail to thermalize the system, leading to persistent quantum states that defy normal thermodynamic laws. Key features of many-body localization: breaks thermalization, meaning energy doesn't spread like it should, preserves quantum information, which is useful for quantum computing and long-term storage of quantum states, exists in highly disordered systems, where interactions prevent particles from escaping their local regions. Why is MBL important? It offers a potential way to create stable quantum memory, where quantum states remain intact for much longer than usual. It challenges conventional ideas of thermal equilibrium and ergodicity, meaning that some quantum systems don't behave like classical systems at all. It could help in designing error-resistant quantum processors, as localized quantum states are less likely to be disturbed by environmental noise. MBL is a cutting-edge topic in quantum physics with deep implications for quantum computing, condensed matter physics, and the foundations of statistical mechanics. Level 69. Entanglement entropy. Entanglement entropy is a way of measuring how much quantum information is shared between different parts of a system. It tells us how entangled a system is, which is crucial for quantum computing, black hole physics, and condensed matter physics. In classical physics, information is straightforward. Either something is known or it isn't. But in quantum mechanics, information is spread out across entangled particles, making it harder to define where one piece of information ends and another begins. Entanglement entropy is particularly important in quantum information theory, where it helps quantify the usefulness of quantum states for computation. Black hole physics, where it plays a role in the black hole information paradox. If black holes destroy information, what happens to entanglement? Quantum phase transitions, where it helps identify exotic states of matter. A famous result in this field is the Ryu-Takayanagi formula, which links entanglement entropy to the geometry of spacetime in holographic theories. This suggests that quantum entanglement may be fundamental to the structure of the universe itself. By studying entanglement entropy, physicists are uncovering new links between quantum mechanics, gravity, and information theory, possibly leading to a deeper understanding of reality itself. Level 70. Quantum Zeno effect. The quantum Zeno effect is a bizarre quantum phenomenon where frequent observation of a system prevents it from changing. It's named after Zeno's paradox, which describes how constant measurement of motion might seemingly prevent movement. In quantum mechanics, this means that if you measure a quantum state repeatedly in rapid succession, you can freeze it in place. Instead of evolving as it normally would, the wave function collapses to the same state over and over, effectively preventing change. This effect has been experimentally observed in atomic physics, where repeated laser pulses prevent atoms from decaying; quantum computing, where it helps in error correction by stabilizing quantum states; biology, where some theories suggest quantum Zeno-like effects might play a role in photosynthesis and neural processing. Interestingly, the opposite effect, the anti-Zeno effect, can also occur, where frequent observation actually accelerates quantum transitions instead of slowing them down. The quantum Zeno effect challenges classical notions of time and measurement, providing a direct demonstration of how observation itself affects quantum reality. It is being explored for applications in quantum computing, secure communication, and controlling quantum systems with precision. Level 71. Weak measurement. Weak measurement is a quantum technique that allows us to gather partial information about a system without fully collapsing its wave function. Unlike traditional quantum measurements, which force a system into a definite state, causing wave function collapse, weak measurements gently extract information while still allowing the system to evolve quantum mechanically. In classical physics, measuring an object does not change it, but in quantum mechanics, standard measurements disturb the system completely. Weak measurement, however, only slightly affects the quantum state, allowing multiple observations over time without completely destroying superposition or entanglement. Key properties of weak measurements. Partial state information. Instead of fully collapsing the wave function, weak measurement gives limited data, which can be averaged over multiple measurements. Preserves coherence. Unlike strong measurement, it allows a quantum system to continue evolving. Useful for precision experiments. Can be used to measure tiny effects, such as shifts in quantum states that would otherwise be lost in noise. Weak measurements are used in quantum optics, quantum computing, and experiments on fundamental quantum mechanics. They help explore quantum paradoxes, such as versions of Schrödinger's cat, where the collapse of the wave function is not abrupt but gradual. Level 72. Quantum non-demolition measurements. Quantum non-demolition (QND) measurements allow scientists to measure a quantum system without destroying the property being measured. In normal quantum mechanics, measuring a system often disturbs it, but QND techniques are designed to avoid this problem. The idea behind QND is that some quantum observables, such as photon number or spin direction, can be measured indirectly in a way that does not disturb their future evolution. This allows for repeated measurements without altering the quantum state significantly. Applications of QND measurements: quantum optics, used to measure photon numbers in lasers without absorbing the light; gravitational wave detection, LIGO, and other experiments use QND methods to improve sensitivity without disturbing the measured signals. Quantum computing helps in error correction by detecting qubit errors without disrupting their quantum state. QND measurements provide a crucial advantage in quantum technologies by allowing information to be extracted while preserving coherence, a key requirement for future quantum systems. Level 73. Spin-orbit coupling. Spin-orbit coupling (SOC) is an interaction where a particle's spin and motion, orbit, are linked together due to relativistic effects. In simpler terms, how an electron moves around an atom can affect its intrinsic spin direction, and vice versa. SOC is a fundamental effect in atomic physics, solid-state physics, and quantum materials. It explains fine structure in atomic spectra, the small shifts in electron energy, levels in atoms arise due to SOC, topological insulators, materials where SOC leads to surface, states that conduct electricity without resistance. Spintronics, a technology where SOC is used to manipulate electron spins for more efficient computing and data storage. One famous consequence of SOC is the Rashba effect, where an applied electric field can split electron spins in certain materials, leading to potential applications in quantum computing and low-power electronics. Spin-orbit coupling is a key ingredient in advanced materials and future quantum devices, as it allows for the precise control of electron spin, opening new possibilities in information processing and energy-efficient electronics. Level 74. Parity violation. Parity violation refers to the fact that the laws of physics are not always symmetric under mirror reflection. In classical physics, if you replace a system with its mirror image, parity transformation, the system's behavior remains unchanged. However, in quantum physics, particularly in the weak nuclear force, this symmetry is broken. This discovery was made in the 1950s by Chien-Shiung Wu in an experiment with cobalt-60 atoms. When cobalt-60 undergoes beta decay, the emitted electrons preferentially travel in a specific direction relative to the atom's spin, proving that nature does not treat left and right equally. Why is parity violation important? Weak force uniqueness. The weak nuclear force is the only known force that violates parity, making it fundamentally different from electromagnetism and gravity. Neutrino physics. Parity violation helped confirm that neutrinos have a well-defined handedness. Always left-handed for neutrinos and right-handed for antineutrinos. Explaining fundamental symmetries. It plays a role in understanding how the universe distinguishes between different types of particles and interactions. Parity violation is one of the most surprising discoveries in quantum physics, challenging the idea that nature treats all directions equally. It remains crucial in high-energy physics, particle accelerators, and the study of fundamental forces. Level 75. CP violation. CP violation refers to the idea that the laws of physics are not always symmetric when you combine charge conjugation C and parity P transformations. Charge conjugation swaps particles with their antiparticles, while parity is the mirror reflection operation. If physics were perfectly symmetric, flipping both charge and parity together, CP symmetry, should leave fundamental interactions unchanged. But experiments show this is not always true. Why does CP violation matter? Matter-antimatter asymmetry. One of the biggest mysteries in cosmology is why the universe contains mostly matter instead of equal amounts of matter and antimatter. CP violation provides a possible explanation for how the imbalance arose in the early universe. Kaon and B meson decay. CP violation was first observed in kaons, a type of subatomic particle, in 1964, and later in B mesons. These observations earned a Nobel Prize and confirmed that fundamental physics is not perfectly symmetric. Standard model tests. CP violation is a key feature in testing and expanding the standard model of particle physics, with possible links to new physics beyond the standard model. Physicists are still searching for additional sources of CP violation that might fully explain the missing antimatter problem in the universe. If a stronger form of CP violation exists, it could lead to the discovery of new particles or interactions, potentially reshaping our understanding of the cosmos. Level 76. Time reversal. Symmetry. Time reversal symmetry is the idea that the fundamental laws of physics should work the same whether time moves forward or backward. In classical physics, most equations are time reversible, meaning if you reverse time in a system, it should behave the same way as before. However, in quantum mechanics and particle physics, some processes do not obey time reversal symmetry. This is most evident in CP violation. Since charge, C, and parity, P violation, are observed in weak interactions, and time reversal, T symmetry, is related to CP symmetry, this suggests that time symmetry is also broken in certain cases. Thermodynamics and entropy. The arrow of time in thermodynamics shows that entropy always increases, making time reversal symmetry unlikely in macroscopic systems. Quantum systems. Some quantum materials and exotic states of matter show effects that depend on whether time moves forward or backward. Why does time reversal symmetry matter? It helps in understanding fundamental physics and how particles interact. It plays a role in designing time reversal invariant quantum materials, such as topological insulators. If time symmetry violations exist beyond what is currently observed, they could provide clues to new physics beyond the standard model. The study of time reversal symmetry is crucial in both high-energy physics and condensed matter physics, revealing deeper insights into the nature of reality. Level 77. Quantum coherence. Quantum coherence refers to the ability of a quantum system to exist in a superposition of states and maintain well-defined phase relationships between those states. This is what makes quantum mechanics so different from classical physics. When a system maintains coherence, it can exhibit quantum interference and entanglement, both of which are key for quantum computing, where maintaining coherence is necessary for running quantum algorithms. Quantum cryptography, where secure quantum communication relies on preserving coherent quantum states. Superconductivity and superfluidity, where coherent quantum states allow particles to move without resistance. However, quantum coherence is fragile. It can be lost due to decoherence, which happens when a system interacts with its environment. This is one of the biggest challenges in building practical quantum computers, since decoherence leads to errors in quantum calculations. Scientists are actively developing ways to extend coherence times using error correction techniques, ultra-cold environments, and topological quantum states to build more stable quantum technologies. Level 78. Quantum interference. Quantum interference occurs when quantum states combine in ways that either amplify or cancel out probabilities. This is one of the most fundamental and mind-bending aspects of quantum mechanics. A famous example is the double-slit experiment, where electrons or photons pass through two slits and create an interference pattern, even when fired one at a time. This proves that particles act like waves and can exist in superposition before being measured. Key applications of quantum interference include quantum computing. Algorithms like Shor's algorithm use interference to speed up problem solving. Quantum sensors. Interference-based devices can measure tiny changes in gravity, magnetic fields, and temperature with extreme precision. Quantum cryptography. Secure key distribution systems use interference effects to detect eavesdropping. Quantum interference is what allows quantum mechanics to outperform classical physics in computation, sensing, and secure communication. It is a crucial ingredient in the next generation of quantum technologies. Level 79. Coherent control. Coherent control is a technique used to manipulate quantum states using light or other external fields. Instead of letting quantum systems evolve randomly, scientists use carefully designed laser pulses or electric fields to steer quantum processes toward a desired outcome. For example, using coherent control, scientists can direct chemical reactions at the quantum level by controlling electron movement, improve quantum computing operations by controlling qubits with high precision, enhance quantum sensing and imaging by controlling how light interacts with molecules. One major application is ultra-fast laser pulses, which can selectively excite atoms and molecules to control their behavior. This is important in fields like quantum chemistry, materials science, and photonics. Coherent control gives scientists unprecedented power over quantum mechanics in action, opening up new possibilities in quantum computing, precision medicine, and molecular engineering. Level 80. Optical lattices. Optical lattices are artificial crystals made from intersecting laser beams that trap and arrange atoms in a grid-like pattern. These lattices allow scientists to simulate and study quantum systems in ways that would be impossible in natural materials. Key features of optical lattices: they create artificial solids, where atoms behave similarly to electrons in real materials. They allow precise control over interactions, making them ideal for studying quantum phase transitions, superfluidity, and topological states of matter. They can be used to simulate exotic physics, such as high-temperature superconductivity or black hole analogues. Applications of optical lattices. Quantum simulators. Optical lattices provide a testbed for exploring strongly correlated quantum systems. Atom-based quantum computing. Arrays of atoms in optical lattices can act as qubits for scalable quantum computing. Precision metrology. Optical lattice clocks are among the most accurate timekeeping devices in the world. Optical lattices have revolutionized quantum physics research, helping scientists probe fundamental quantum effects, develop new materials, and push the limits of precision measurement. Level 81. Cold atom physics. Cold atom physics is the study of atomic gases that have been cooled to ultra-low temperatures, often near absolute zero. At these extreme temperatures, atoms move incredibly slowly, allowing researchers to study quantum effects that would normally be hidden by thermal motion. Using techniques like laser cooling and magnetic trapping, scientists can cool atoms down to just a few billionths of a degree above absolute zero. At this point, atoms start behaving like quantum matter waves instead of classical particles. Key breakthroughs in cold atom physics: Bose-Einstein. Condensates, BECs. A state where atoms merge into a single quantum wave, allowing for studies of superfluidity and quantum coherence. Optical lattices, laser-created grids that trap atoms, mimicking the behavior of electrons in solid materials. Atom interferometry. Cold atoms are used to make ultra-precise sensors for detecting gravity, rotation, and magnetic fields. Cold atom physics is essential for quantum simulations, quantum computing, and precision measurement. By studying these ultra-cold systems, scientists can probe fundamental physics, including models of black holes, early universe conditions, and quantum many-body effects. Level 82. Ion traps. Ion traps are devices that use electric and magnetic fields to confine charged atoms, ions, in space, allowing precise control over their quantum states. Trapped ions are among the leading platforms for quantum computing and high-precision timekeeping. There are two main types of ion traps. Paul traps use oscillating electric fields to confine ions. Penning traps use a combination of static magnetic and electric fields. Why are ion traps important? Quantum computing. Individual trapped ions serve as qubits with extremely long coherence times and high-fidelity operations. Atomic clocks, ion-based clocks, are among the most accurate in the world, keeping time to within a fraction of a second over millions of years. Fundamental physics. Ion traps allow for precision tests of quantum mechanics, such as measuring fundamental constants and searching for possible variations in physical laws. Ion trap technology is at the forefront of quantum information science, providing one of the most promising platforms for building scalable, fault-tolerant quantum computers. Level 83. Rydberg atoms. Rydberg atoms are atoms where an electron has been excited to an extremely high energy level, making the atom much larger than usual, sometimes hundreds or even thousands of times larger than a normal atom. These highly excited atoms have unusual quantum properties, including strong interactions. Rydberg atoms interact strongly with each other, making them useful for quantum computing and quantum simulation. Long lifetimes. Since their electrons are far from the nucleus, they remain in their excited states for relatively long periods. Extreme sensitivity. They are highly sensitive to electric and magnetic fields, making them useful for quantum sensors. Applications of Rydberg atoms. Quantum computing. Rydberg states are used to create entanglement between atoms, forming a basis for scalable quantum logic gates. Quantum simulation. They can model exotic many-body quantum systems, such as topological materials and high-temperature superconductors. Fundamental physics, used in tests of quantum electrodynamics, QED, and searches for new physics beyond the standard model. Rydberg atoms are a powerful tool in quantum technologies, offering new ways to control, manipulate, and study quantum interactions. Level 84. Cavity quantum electrodynamics, cavity QED. Cavity quantum. Electrodynamics cavity QED studies the interaction between light, photons, and matter, atoms, ions, or superconducting circuits inside a highly reflective cavity. This creates an environment where quantum effects dominate. In classical optics, light and matter interact continuously. In cavity QED, however, interactions happen in a controlled, quantized manner, where individual photons can be manipulated to influence atoms at the quantum level. Key effects in cavity QED: strong coupling. A single atom can strongly interact with a single photon, leading to controlled quantum entanglement. Quantum state engineering allows precise control over quantum states of light and matter. Non-classical light sources, cavity QED, enables the creation of single photon sources needed for quantum communication and quantum cryptography. Applications of cavity QED: quantum networks, connecting quantum computers over long distances using entangled photons. Fundamental tests of quantum mechanics, studying wave-particle duality and quantum measurement. Ultrasensitive detectors, detecting extremely weak signals, useful in astrophysics and metrology. Cavity QED has played a major role in the development of quantum optics, quantum computing, and quantum communication, helping bridge the gap between classical and quantum information processing. Level 85. Quantum simulation. Quantum simulation is the use of quantum systems to model complex physical problems that are too difficult for classical computers. Instead of solving equations numerically, a quantum simulator directly mimics the behavior of a quantum system, providing insights into many-body physics, high-energy physics, and material science. Why use quantum simulation? Classical computers struggle with quantum problems. Simulating quantum systems, like interacting electrons in materials, requires massive computational power, but quantum simulators can do this naturally. Understanding exotic materials. Quantum simulators can help design high-temperature superconductors and new quantum materials. Probing fundamental physics, simulating black holes, early universe conditions, and new quantum phases of matter. Platforms for quantum simulation. Cold atoms in optical lattices mimic electron behavior in solids. Trapped ions can model interacting quantum spins. Rydberg atom arrays used to simulate exotic many-body quantum effects. Quantum simulation is one of the most promising near-term applications of quantum technology, with the potential to revolutionize material science, chemistry, and fundamental physics by providing insights into problems that classical computing cannot solve. Level 86. Quantum annealing. Quantum annealing is a specialized form of quantum computing that solves optimization problems by finding the lowest energy state of a system. Instead of using quantum gates like conventional quantum computers, quantum annealers use superposition and tunneling to explore many possible solutions simultaneously. How quantum annealing works. The system starts in a superposition of all possible solutions. A problem is encoded into the system's energy landscape, where lower energy states correspond to better solutions. The system gradually evolves toward its lowest energy state, which represents the optimal solution to the problem. Why is quantum annealing important? Optimization problems, used in logistics, finance, machine learning, and AI to find optimal solutions faster than classical methods. Material science helps simulate molecular structures to discover new materials. Machine learning can improve AI models by optimizing large datasets efficiently. The best-known quantum annealer is D-Wave, which has built commercial quantum machines specifically designed for solving optimization problems. While not a universal quantum computer, quantum annealing shows promise for solving real-world problems in industry and science. Level 87. Adiabatic quantum computing. Adiabatic quantum computing, AQC, is a computational model that gradually transforms a simple quantum system into a more complex one to solve problems. It is closely related to quantum annealing, but has broader applications. How does it work? The system begins in the ground state, lowest energy state, of a simple quantum problem. The Hamiltonian energy function of the system is slowly changed to match the problem that needs solving. By following the adiabatic theorem, the system remains in the lowest energy state throughout the process, meaning it naturally evolves into the correct answer. Applications of AQC optimization problems, similar to quantum annealing but with more general computing capabilities. Quantum simulation can model complex quantum systems found in nature. Cryptography helps solve problems in cryptographic security. While not yet as widely developed as gate-based quantum computing, AQC provides a promising alternative pathway to practical quantum computation, with potential applications in science and industry. Level 88. Topological quantum computing. Topological quantum computing is a highly advanced approach to quantum computing that uses exotic particles called anyons to encode and process information in a way that is naturally resistant to errors. Unlike conventional quantum computers, which use delicate qubits that are easily disturbed, topological quantum computing stores information in braided quantum states, making it much more stable against environmental noise. How it works. Anyons, special quasi-particles, exist in two-dimensional materials and have unique quantum properties. When these anyons move around each other, their paths form braids that encode quantum information. Since these braids are topological, small disturbances in the system do not destroy the information. Why is it important? Error resistance. Topological quantum computers are naturally protected from many types of quantum noise. long coherence times. Because information is stored in a global rather than a local property, decoherence is less of a problem. Scalability could enable more practical and large-scale quantum computers. Microsoft has invested heavily in Majorana-based topological qubits, but this field is still in the experimental stage. If successful, topological quantum computing could be a major breakthrough in creating fault-tolerant quantum processors. Level 89. Majorana fermions. Majorana fermions are exotic quantum particles that act as their own antiparticles, meaning that they are neutral and do not have distinct particle-antiparticle pairs. Why are they special? They were first predicted by Ettore Majorana in 1937 and have been a major focus of research ever since. Unlike regular fermions, like electrons, Majorana fermions do not obey conventional particle-antiparticle behavior. They can exist in special quantum materials, such as topological superconductors, and are promising candidates for topological quantum computing. Majorana fermions are interesting for two major reasons. Fundamental physics. If detected, they could help explain why neutrinos have mass and even provide insights into dark matter. Quantum computing. Majorana fermions create Majorana zero modes, which can be used in fault-tolerant topological quantum computers. Although experimental evidence for Majorana fermions is still debated, their discovery would have profound implications for both fundamental physics and quantum technology. Level 90. Quantum teleportation. Quantum teleportation is a method of transmitting quantum information from one place to another without physically moving the particle itself. Instead, it uses entanglement to instantaneously transfer quantum states. How it works. Two particles, let's call them A and B, are entangled and then separated. A third particle, C, has a quantum state that we want to teleport. A measurement is made on A and C, collapsing their states into a new form. Because B is entangled with A, the quantum state of C instantly appears in B, even if it is far away. Key facts about quantum teleportation: no faster than light communication. Although teleportation is instantaneous, classical information is still needed to reconstruct the state at the receiving end. Used in quantum networks. Quantum teleportation is a key part of quantum communication, quantum encryption, and future quantum internet infrastructure. Does not teleport matter. Unlike in science fiction, quantum teleportation only transmits information, not physical particles. Quantum teleportation has already been demonstrated in laboratories and space, with experiments teleporting quantum states over hundreds of kilometers. In the future, it could be used to create ultra-secure global quantum networks. Level 91. Entanglement swapping. Entanglement swapping is a quantum process that allows two particles to become entangled without ever directly interacting. This is a key concept for building large-scale quantum networks and quantum teleportation systems. How it works. Start with two pairs of entangled particles, A1, A2, and B1, B2. A measurement is performed on A2 and B1, which destroys their individual entanglement, but creates a new entangled link between A1 and B2. Even though A1 and B2 never interacted, they are now entangled and can be used for quantum communication. Why is entanglement swapping important? It allows entanglement to be extended over long distances, essential for quantum communication. It forms the basis for quantum repeaters, which are necessary for building a quantum internet. It enables secure quantum networks, where distant parties can share encryption keys through entanglement. Entanglement swapping is already being tested in satellite-based quantum communication and is expected to be a core technology in future global quantum networks. Level 92. Quantum repeaters. Quantum repeaters are devices that extend the range of quantum communication by counteracting decoherence and loss over long distances. In classical networks, repeaters amplify signals to prevent data loss. However, Quantum states cannot be copied due to the no-cloning theorem, so a different method is needed. Quantum repeaters solve this problem by generating entanglement between distant nodes using entanglement swapping, storing and purifying quantum states to remove errors caused by environmental noise, relaying entanglement step by step until the entire network is linked. Why are quantum repeaters important? They enable secure quantum communication over thousands of kilometers, essential for a global quantum internet. They improve quantum key distribution, QKD, making cryptographic systems unbreakable. They allow quantum teleportation over long distances, opening the door for fully quantum networks. Currently, quantum repeaters are a major focus in research, with experimental demonstrations proving their potential for large-scale quantum communication systems. Level 93. Quantum networks. A quantum network is a system that connects quantum devices like quantum computers or sensors using entanglement and quantum communication. Unlike classical networks that transmit bits, quantum networks transfer quantum states securely across distances. Core components of quantum networks. Quantum repeaters extend the reach of entanglement-based communication. Entanglement swapping links distant nodes without direct interaction. Quantum key distribution, QKD, ensures unbreakable encryption for secure communication. Quantum teleportation allows quantum states to be transferred without physical transmission. Potential applications. Quantum Internet, a future network where quantum devices communicate securely. Ultra-secure communication. Governments and banks could use quantum encryption that is impossible to hack. Distributed quantum computing. Multiple quantum computers could work together by sharing entangled states. Experiments like China's MISHA satellite have already demonstrated quantum networks on a large scale, paving the way for global quantum communication. Level 94. Decoherence-free subspaces. Decoherence-free subspaces, DFS, are special quantum states that are naturally resistant to environmental noise, making them crucial for building robust quantum computers and networks. Quantum systems are extremely fragile, and interactions with the environment cause decoherence, which destroys quantum information. However, some quantum states can be arranged in a way that makes them immune to certain types of noise. These are known as decoherence-free subspaces. How DFS works. Certain symmetries in the environment cause specific noise types to cancel out. By encoding quantum information in these noise-resistant states, we can protect qubits from errors. Unlike active error correction, which requires extra qubits for redundancy, DFS provides passive protection against decoherence. Applications: fault-tolerant quantum computing. Reduces the need for complex quantum error correction. Long-distance quantum communication keeps quantum states stable during transmission. Quantum sensors improves the precision of measurements by reducing external interference. By taking advantage of decoherence-free subspaces, researchers are working toward more stable and practical quantum technologies. Level 95. Quantum thermodynamics. Quantum thermodynamics is the study of how quantum systems exchange energy, obey entropy laws, and perform work at the microscopic level. Classical thermodynamics describes how heat and energy behave in large systems, but at the quantum level things get much stranger. Key concepts in quantum thermodynamics. Quantum heat engines, devices that use quantum effects to convert heat into work, potentially more efficiently than classical engines. Quantum Maxwell's Demon, a thought experiment exploring whether quantum information can be used to extract energy from a system. Quantum entropy measures disorder in quantum systems, influencing how information spreads. Why is quantum thermodynamics important? It helps in designing energy-efficient quantum technologies. It provides insights into quantum information theory and the limits of computation. It plays a role in understanding black hole thermodynamics, including Hawking radiation. Quantum thermodynamics is a rapidly growing field that connects quantum mechanics, information theory, and energy science with applications in nanotechnology, quantum computing, and even cosmology. Level 96. Quantum biology. Quantum biology explores the role of quantum mechanics in living systems, investigating how biological processes might rely on quantum effects, such as superposition, entanglement, and tunneling. Unlike classical biology, which explains life in terms of chemical and molecular interactions, quantum biology suggests that some fundamental life processes operate on a quantum scale. One of the most well-known examples of quantum biology is photosynthesis. In plants, light energy is captured by molecules and efficiently transferred to reaction centers, where it is converted into chemical energy. Experiments suggest that this energy transfer is not a random process, but a quantum coherent event, meaning the energy moves as a wave, exploring multiple paths simultaneously and choosing the most efficient route. Another intriguing application of quantum biology is enzyme catalysis, where quantum tunneling may allow particles to bypass energy barriers, speeding up reactions in ways that classical chemistry cannot fully explain. There is even evidence suggesting that quantum entanglement plays a role in bird navigation, as certain migratory birds use the Earth's magnetic field to orient themselves, possibly through entangled electron spins in specialized proteins in their eyes. Although quantum biology is still in its early stages, it challenges the assumption that quantum effects disappear in warm, wet environments. If quantum processes indeed play a role in life, understanding them could lead to breakthroughs in medicine, bioengineering, and even the origins of consciousness. Level 97. Quantum chaos. Quantum chaos is the study of how classical chaos theory applies to quantum systems. In classical physics, chaos refers to systems that are highly sensitive to initial conditions, such as weather patterns or planetary orbits. However, in quantum mechanics, things behave differently. While quantum systems can exhibit chaotic-like behavior, they never truly become unpredictable in the classical sense. One of the key challenges in quantum chaos is understanding how classical chaotic behavior emerges from quantum laws. Unlike classical systems that experience exponential divergence of trajectories, quantum systems evolve in a more structured way due to the unitary nature of quantum mechanics. However, certain systems, such as highly excited atoms in strong magnetic fields, exhibit signatures of chaos, such as random energy level distributions and complex wave function patterns. Quantum chaos is not just a theoretical curiosity, it has real-world implications for quantum computing, nuclear physics, and black hole physics. Recent studies suggest that black holes may be among the most chaotic quantum systems in the universe, with implications for information scrambling and the black hole information paradox. Understanding quantum chaos may also help improve quantum error correction, ensuring that quantum computers remain stable even in complex environments. Level 98. Quantum information theory. Quantum information theory is the study of how information is stored, transmitted, and processed in quantum systems. It extends classical information theory, which underpins digital computing and communication, into the quantum realm, where qubits, entanglement, and superposition create entirely new possibilities for computing and cryptography. One of the most revolutionary aspects of quantum information theory is quantum computing, where quantum bits, qubits, allow for massive parallelism in computation. Unlike classical bits that can only be 0 or 1, qubits can exist in a superposition of both states, enabling quantum computers to solve certain problems exponentially faster than classical machines. Quantum information theory also forms the foundation for quantum cryptography, particularly quantum key distribution QKD, which allows two parties to share encryption keys in a way that is fundamentally unbreakable due to the laws of physics. Another key concept is quantum entanglement as a resource, meaning entangled particles can be used to perform communication and computation tasks that are impossible in classical systems. The field also studies quantum error correction, ensuring that quantum information remains intact despite the fragile nature of qubits. As quantum technology advances, quantum information theory is expected to reshape computing, security, and fundamental physics, unlocking new ways to process and secure information in the quantum age. Level 99. Emergent quantum phenomena. Emergent quantum phenomena occur when collective quantum behavior leads to new properties that cannot be explained by individual particles alone. This is a core idea in modern physics. Simple quantum rules at the microscopic level can give rise to completely new physical effects at larger scales, often with profound technological applications. One of the most striking examples of emergent quantum phenomena is superconductivity, where electrons form pairs that move without resistance, allowing for perfect electrical conduction. Similarly, superfluidity arises when quantum particles behave collectively, forming a liquid that flows without viscosity. Another example is topological matter, where certain materials exhibit exotic properties, such as edge currents that remain stable against disorder, laying the foundation for topological quantum computing. Emergent quantum phenomena are also central to understanding the early universe and exotic states of matter, such as quark-gluon plasmas, strange metals, and high-temperature superconductors. As research advances, studying emergent quantum behavior could lead to revolutionary applications in energy transmission, quantum computing, and even next-generation electronics. Level 100. The quantum universe. At the deepest level, the entire universe may be fundamentally quantum. While classical physics describes the macroscopic world we see, quantum mechanics governs everything at the smallest scales, from subatomic particles to the very fabric of spacetime. Understanding how quantum mechanics applies to cosmology, black holes, and the structure of space and time itself remains one of the greatest scientific challenges. One of the most profound quantum ideas in cosmology is quantum fluctuations in the early universe. During the Big Bang, tiny quantum fluctuations expanded due to cosmic inflation, shaping the large-scale structure of galaxies we see today. Additionally, black holes appear to be deeply connected to quantum mechanics. Stephen Hawking's discovery of Hawking radiation showed that black holes can emit quantum particles and eventually evaporate, raising deep questions about the fate of information in the universe. Quantum mechanics may also hold the key to unifying gravity with the other fundamental forces. Current attempts such as string theory and loop quantum gravity seek to describe spacetime itself as a quantum entity, where gravity emerges from deeper quantum structures. If successful, such theories could revolutionize our understanding of reality and perhaps even lead to new insights about the multiverse, the nature of time, and the fabric of existence itself. At its core, quantum mechanics challenges everything we think we know about reality. It suggests that the universe is not deterministic, but probabilistic, that observation affects reality, and that everything may be fundamentally connected through entanglement. As we continue to explore the quantum universe, we may not just unlock new technologies, but also uncover the very foundations of existence itself.